Welcome to this course, where we will methodically prepare you for the Splunk Observability Cloud Metrics User Certification. This initial segment acts as your foundational guide to understanding both the exam structure and the practical telemetry concepts required to succeed. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to Splunk Inc. in any way. All trademarks, including Splunk and the SPLK-4001 exam name, belong to their respective owners. In this opening chapter, we will align our expectations with the official certification blueprint to ensure every minute of your study time delivers maximum value. We intend to deconstruct the core competencies mandated by the SPLK-4001 examination, transforming high-level objectives into actionable technical knowledge you can apply immediately. By the end of this journey, you will possess not only the theoretical clarity needed for the test, but also the hands-on proficiency to navigate complex observability environments. Our approach prioritizes deep understanding over rote memorization, helping you grasp the why behind the metrics and the how of effective cloud monitoring. This is the strategic architectural framework you need to systematically master telemetry ingestion, visualization, and operations. To begin our preparation, we must acknowledge that the SPLK 4001 exam is designed to validate your ability to operate within a cloud-native monitoring landscape. The examination typically consists of a series of multiple-choice and multiple-response questions, constrained by a strict time limit that demands both speed and precision. You should expect to see items weighted heavily toward your understanding of how data enters the Splunk observability pipeline, how it is transformed, and how it is ultimately surfaced to the end user. It is not merely about clicking buttons in an interface. It requires a functional grasp of metric types, dimensionality, and the fundamental mechanics of time series data. We will work through the architectural nuances of the OpenTelemetry collector and the subsequent processing pipelines, which serve as the primary conduits for your system's observability data. As we progress through the curriculum, we will map every module directly to the core competencies outlined by Splunk. We assume you have a baseline familiarity with Linux environments and basic infrastructure concepts, as these serve as the foundation for the deployment of collection agents. Throughout our discussions, we will strictly follow the logic dictated by the official exam roadmap, ensuring that no topic is left unexplored or poorly contextualized. We will look closely at how detectors function, how alerts are triggered by specific signal patterns, and how visualizations allow you to interpret high-cardinality data effectively. By segmenting our learning into ingestion, architecture, visualization, and orchestration, we provide the structure necessary to absorb complex concepts without feeling overwhelmed by the sheer volume of features. Reliability and observability comes from a rigorous understanding of how data is structured and stored within the platform. We will explore the life cycle of a data point, from the moment it is emitted from your source to the point where it becomes a rendered chart on a dashboard. This involves understanding the importance of metadata and tags, which define the dimensionality that makes your metrics searchable and actionable. You will learn to navigate the built-in content effectively, leveraging pre-configured dashboards before moving into the customization phase, where you build your own analytics. This progression mimics real-world scenarios where you must first understand the default platform behavior before you can extend it to meet specific operational requirements. Finally, we will address the challenges of high-scale environments where alert fatigue is a persistent risk. You will learn how to refine detector logic to ensure that your alerts are meaningful, context-rich, and targeted. We will cover the orchestration of muting rules and the application of analytic transformations that allow you to distinguish signal from noise in a noisy environment. The goal is to equip you with the technical vocabulary and the analytical methodology required to pass the exam and function competently as a Splunk Observability Cloud practitioner. Prepare to dive into the technical details with precision and focus as we lay the groundwork for your upcoming certification. Let's begin our journey into effective telemetry management. See you in the next lesson. Welcome to this deep dive into the OpenTelemetry core architecture, where we will establish the foundations for your mastery of observability data. You are about to unlock the vendor-agnostic power of OpenTelemetry, providing you with the exact technical knowledge required to pass your certification exam and manage complex observability pipelines with full confidence. To understand the OpenTelemetry ecosystem, we must first distinguish between the three primary telemetry streams: logs, traces, and metrics. Logs represent discrete, time-stamped events that capture significant occurrences within an application, while traces document the causal path of a request as it traverses various service boundaries. Metrics, conversely, are numerical representations of measurements captured over time, providing the aggregate data necessary to understand the health and performance of your infrastructure. OpenTelemetry provides a unified specification that allows these three signals to be collected, transformed, and exported without binding your implementation to a single vendor. Whether you are working with legacy monorepos or modern microservices, the underlying goal is to decouple your instrumentation from your backend storage layer. This separation is the key to maintaining a sustainable observability strategy that evolves alongside your software architecture. The architecture of OpenTelemetry is defined by strict specifications that govern both the API and the SDK execution planes. The API serves as the interface used by developers to instrument their code, while the SDK is the concrete implementation that processes the telemetry data by handling aggregation, batching, and exporting. One of the most important concepts to master is the semantic convention, which provides a standard naming schema for attributes across different systems. By adhering to these conventions, you ensure that your attributes, such as resource identifiers or HTTP status codes, remain consistent regardless of the underlying language or deployment platform. This consistency is essential when you move towards centralized analysis, as it guarantees that downstream systems can correctly parse and correlate data from disparate sources. Without these conventions, the data would remain fragmented, making it impossible to perform effective cross-service diagnostics. Instrumentation packages and resource definitions exist as separate but symbiotic components within the OpenTelemetry framework. An instrumentation package encapsulates the logic required to capture specific signals from a library or host, essentially serving as a plugin that sits between your code and the data pipeline. Resource definitions, on the other hand, provide the metadata regarding the environment itself, such as the hostname, container ID, or service version. When these resources are combined with instrumentation data, they provide the necessary context to understand exactly where a metric originated within your infrastructure. The ingestion pipeline acts as the physical abstraction that processes these contexts, moving data from the point of origin through various intermediate processors before reaching its destination. Understanding this movement is crucial because it allows you to define where data should be filtered, dropped, or enriched with additional metadata before it is stored. Distributed contexts form the backbone of the OpenTelemetry processing lifecycle, ensuring that metadata is propagated correctly throughout an entire system. When a request travels from a client to a server or across a distributed service mesh, the context propagates this information so that every downstream component understands the original caller's state. This mechanism is primarily responsible for stitching traces together, but it also provides the necessary identifiers that allow metrics to be aggregated by specific service instances or zones. Because this architecture is inherently decoupled, it allows you to swap or upgrade your observability backend without modifying a single line of instrumentation code in your applications. This vendor-agnostic control is a primary design goal for modern infrastructure, effectively preventing lock-in while maintaining the integrity and quality of your telemetry signals. By analyzing these pipeline definitions, you gain the ability to troubleshoot data loss or inconsistent reporting at any stage of the telemetry journey. See you in the next lesson. Welcome back, and today we begin our exploration into deploying the OpenTelemetry collector within Linux production environments. This chapter focuses on the architectural rigor required to achieve stable, high-performance telemetry ingestion across your fleet. Deploying the OpenTelemetry collector on Linux requires a deliberate approach that prioritizes security and process stability over simple convenience. While many distributions offer package manager wrappers, production environments often demand the granularity that comes with direct binary execution or custom shell-based automation. When you utilize the standard shell installation scripts provided by the distribution channel, you are essentially establishing a repeatable state for the collector binary. The primary objective is to place the executable in a controlled location, typically within standard path variables like SSA, local/bin, while ensuring that the collector runs with a dedicated service account. Establishing a non-privileged system user for the collector process is a non-negotiable security requirement that prevents the telemetry agent from inheriting root-level permissions during runtime. Once the binary is correctly placed, our focus shifts toward containerization-style process management using systemd unit files to handle daemon lifecycle events. Operating the collector as a system-managed daemon ensures that the process survives reboots and maintains a consistent uptime presence on the host. You need to define a unit file that specifies the correct environment variables, including the essential configuration files and runtime flags that dictate how the collector maps to your Observability Cloud ingestion endpoints. When crafting these definitions, pay close attention to the memory and CPU constraints declared within the systemd service file, as these directly influence the resource allocations available to your tracing and metrics pipelines. If you fail to impose these constraints, an aggressive ingestion spike could cause the collector to consume excessive resources, leading to out-of-memory events that destabilize your host operating system. Proper orchestration implies that the daemon initialization state is verified via system-ictl commands, confirming that the service has transitioned to the active and running status before you proceed to validate network connectivity. Securing the pipeline requires meticulous coordination with host-level and network-level firewall configurations to ensure reliable data transmission. Even if the collector service binary is installed and running correctly, you will encounter immediate data loss if the host firewall blocks the outbound traffic needed to reach your ingest gateways. Most Linux environments employ tools like IP tables or firewalled, and you must explicitly define egress rules to allow traffic over specific ports, typically port 4317 for gRPC or 4318 for HTTP. Beyond simple port access, you must also be aware of the runtime environment variables that influence DNS resolution and proxy routing if your organization enforces strict outbound traffic governance. By validating these network paths early in your deployment lifecycle, you eliminate many of the common connectivity errors that plague early-stage metric pipeline stabilization efforts. Finally, the integrity of your telemetry data relies on the stability of the configuration that points your collector to the upstream endpoints. You must ensure that the absolute architecture pathing for your configuration files is correctly referenced in the startup parameters of the daemon, preventing the collector from falling back to default operational settings. Auditing the system resource allocations is not just a one-time task. It should be integrated into your monitoring strategy to ensure that the collector scales appropriately as your metrics ingestion volume increases over time. Stabilizing the pipeline requires an understanding of how the collector interacts with the underlying kernel, specifically regarding how it reads system metadata and processes metrics before they ever leave the host. Once the binary is secure, the service is managed as a daemon, and the network paths are validated, you possess a robust foundation for building advanced ingestion rules later in your lifecycle. See you in the next lesson. Welcome back. In this chapter, we will master the structural configuration of OpenTelemetry pipelines to ensure your observability data flows reliably from your infrastructure to the Splunk Observability Cloud. Configuring ingestion pipelines is fundamentally about defining how data travels from your source through the processor chain and finally to its destination. When working with the OpenTelemetry collector, you're essentially writing a set of instructions in a YAML file that explicitly maps receivers, processors, and exporters. The receiver component is where your telemetry begins its lifecycle. Whether you are utilizing the OTLP receiver for standard trace and metric ingestion, the Prometheus receiver for scraping endpoints, or the host metrics receiver to gather system-level performance data, this is your entry point. Each receiver must be configured with the correct protocol and listening port to ensure that the data actually arrives at the collector process. It is important to remember that these configurations are strict, and even minor errors in indentation will result in a fatal startup failure, preventing the collector from initializing entirely. Once you have defined your sources, you must establish safety guardrails using the memory alimiter processor. This component acts as a proactive defense mechanism, monitoring current memory consumption and dropping incoming data if thresholds are breached, which prevents the collector from being killed by the operating system's out-of-memory killer. After the data has been ingested and memory safety is established, our focus shifts to the processing layer, where the raw data is transformed into meaningful signals. The attributes processor is one of the most frequently used tools here, as it allows you to manipulate, insert, or update metadata on your spans and data points before they are forwarded. For instance, you might use this to append environmental tags, like a production or staging classification, to incoming metrics to enhance your ability to filter them later in Splunk. You have the flexibility to sequence these processors in a specific order within your pipeline configuration, which is critical because data transformations propagate through the chain linearly. The order of operations matters significantly when you are performing tasks like metric aggregation, filtering, or batching. If you place a batch processor after your transformations, you effectively group the process data together, which optimizes the throughput and efficiency of the subsequent egress to the exporter. Think of this pipeline as a digital conveyor belt where each station must be perfectly calibrated to avoid creating bottlenecks or data corruption. The final structural element in your YAML file is the exporter, which dictates where your process telemetry is directed once it leaves the pipeline. Defining multi-endpoint exporter targets allows you to send data to different destinations or backends, providing redundancy and flexibility in your data strategy. Within the OpenTelemetry configuration, the service section serves as the orchestration layer that ties everything together. Here, you formally declare your pipelines, specifying the unique combination of the receivers, processors, and exporters that should execute for each signal type, such as metrics, logs, or traces. A pipeline definition is not merely a label. It tells the collector exactly which data paths to construct at runtime. Because this structure is so rigid, I strongly recommend that you adopt a clean, modular approach to your YAML files, separating concerns where possible so that configuration errors are easier to isolate. As you gain more experience, you will see that debugging a stalled pipeline often starts with checking these service declarations to ensure that the expected exporter is actually mapped to the data type you are trying to transmit. Transitioning towards a reliable ingestion architecture requires you to be comfortable with the specific syntax required by the OpenTelemetry project. While the flexibility is immense, the cost of this flexibility is the need for precise indentation and hierarchical structuring in your configuration files. If you find that the collector refuses to start, the first place to look is always the logs, which will usually point to a line number in your configuration file where a schema validation error occurred. Always validate that your ports are not undergoing conflicts with other processes on the host machine, as a common mistake is attempting to start multiple instances of a collector that all attempt to bind to the same default OTLP port. Understanding these underlying mechanics of ingestion pipelines will serve as your primary defense against data gaps and will ultimately lead to a much more stable observability deployment within your organization. See you in the next lecture. Hello, and welcome back. In this chapter, we will examine how to refine your telemetry data before it reaches your cloud storage. We will explore the technical mechanisms for filtering, transforming, and routing metrics directly within the OpenTelemetry collector pipeline. When we talk about editing processing rules within the OpenTelemetry collector, we are essentially moving the data manipulation logic as close to the source as possible. This approach, often called edge processing, is vital for maintaining a clean and cost-effective observability strategy. By modifying data in transit, we prevent unnecessary overhead in the backend and ensure that our metrics represent the state of our infrastructure accurately. The resource processor is our primary tool for static metadata injection, allowing us to attach context like region or cluster identifiers to incoming data streams. Meanwhile, the transform processor, which leverages the OpenTelemetry transformation language, gives us the power to execute complex modifications, such as attribute renaming or outright removal of high-cardinality metadata. Mastering these tools requires an understanding of how data flows through the collector pipeline, specifically moving from receivers through various processors and finally to chosen exporters. If we fail to curate this data stream effectively, we quickly risk being overwhelmed by noise that complicates our analysis downstream. The configuration syntax must be precise, as even minor errors in the YAML definition of these pipelines can lead to dropped telemetry, or, worse, malformed data ingestion. We treat these configurations as part of our infrastructure code, and they demand the same level of rigor and validation that we apply to our application source code. Metric filtering is perhaps the most immediate tactical application of processing rules, serving as a first line of defense against excessive data ingestion. In scenarios with high cardinality metrics, such as those generated by automated infrastructure, we might find ourselves collecting dimensions that provide no actual analytical value. Using the filter processor, we can explicitly drop these attributes at the collector level, which effectively optimizes our cloud data consumption and keeps our storage footprint manageable. This is not merely about cost, though that is often a primary driver. It is about signal-to-noise ratio. By stripping away extraneous metadata before it reaches the backend, we ensure that queries remain fast and that dashboards remain performant. One common pattern involves the selective inclusion or exclusion of metrics based on their identifiers, allowing us to drop transient data while preserving core health telemetry. It is important to approach this cautiously, keeping in mind that once data is discarded at the edge, it cannot be reconstructed later. Therefore, your filtering logic should be grounded in a clear understanding of the specific dimensions required for your current observability needs. Beyond simple filtering, attribute injection allows us to enrich our sparse incoming data with static environmental context that is otherwise missing from the binary payload. For example, by using the resource processor, we can inject key metadata attributes like environment names, deployment regions, or cluster IDs directly into the span or point data. This creates a more robust analytical model, allowing us to slice and dice our metrics across higher-level groupings in the dashboard interface. This implementation is particularly useful in multi-tenant environments where shared infrastructure might otherwise result in indistinguishable metric streams without proper tagging. Beyond static injection, the transform processor permits dynamic manipulation of existing data through OpenTelemetry transformation language expressions. We can perform operations such as concatenating attributes to form new, unique identifiers, or standardizing numeric values across different services. This capability is instrumental when dealing with heterogeneous upstream sources that share metric names but use inconsistent attribute schemas. By unifying these schemas at the collector level, we perform the necessary normalization that simplifies alert configuration and dashboard consistency across multiple platforms. Conditional routing strategies represent the most advanced edge processing workflow, allowing us to direct specific types of metrics to distinct backend infrastructure or storage endpoints. By leveraging specialized internal metrics routing matrices, we can isolate sensitive telemetry or prioritize critical health signals while diverting bulk performance data elsewhere. This is achieved through well-defined pipeline configurations, where we can specify conditions based on resource attributes or metric names that determine the ultimate destination of the data. Managing this requires a deep understanding of pipeline dependencies, as each processor in the chain adds latency and contributes to overall resource consumption on the collector nodes. We must ensure that our routing logic is safe, preventing infinite loops or unintentional data black holing that could occur if our conditional expressions are not mutually exclusive or well-defined. This control is indispensable for organizations managing large-scale, distributed environments where different teams operate with unique compliance, retention, and performance requirements for their telemetry. Taking control of these routes transforms the collector from a passive bridge into an intelligent telemetry orchestration node. I look forward to seeing you in the next lecture. Welcome back. In this session, we will examine the systematic approach required to troubleshoot and resolve common agent-related errors within your OpenTelemetry collector environment. When we observe telemetry data gaps, the initial focus must be on the internal state of the collector itself. Initialization faults often stem from malformed configuration files where the YAML structure violates the expected schema. I suggest validating your collector configuration using strict syntax checkers before deployment, as even a minor indentation error can silently prevent the pipeline from starting. If the collector hangs during boot, inspect the local internal telemetry log files by increasing the verbosity to the debug level. This adjustment reveals the specific point of failure during initialization, such as an inability to bind to a designated port or an invalid exporter definition. Focusing on these low-level logs allows you to isolate whether the issue is structural or environmental without guessing at the root cause. Communication hurdles often manifest as authentication handshakes that fail when the collector attempts to establish a secure connection to the Splunk Observability Cloud endpoints. You will frequently encounter these issues when working within restrictive enterprise environments that enforce TLS interception through transparent proxies. The core issue here is often an untrusted certificate chain, which appears as a TLS handshake error in your logs. Ensure that your environment's root CA certificates are properly injected into the collector's container or host environment. When you see unauthorized access tokens, verify the integrity of your authentication headers and ensure the secret key has not been rotated or expired. Dissecting the connection lifecycle through network tracing tools can confirm if a proxy is actively terminating the connection before it reaches the backend. Memory utilization remains a primary concern in containerized deployments, particularly when high-throughput metrics cause transient spikes that trigger an killed status. This event occurs when the collector process consumes more memory than the assigned C group limit, causing the kernel to forcefully terminate the process. To diagnose this, I recommend monitoring the internal metrics exported by the collector, specifically focusing on the number of process spans or data points per second. If you observe memory ballooning, review your processing rules to ensure they are not creating excessive copies of incoming data or buffering too many events in memory. Sometimes backpressure handling is configured poorly, causing the collector to retain data indefinitely rather than dropping it or applying rate limiting. Network throughput and packet loss represent another layer of complexity, especially when dealing with high-volume ephemeral infrastructure. You may encounter instances where data packets are dropped before they even leave the host, which is often symptomatic of kernel-level issues like buffer overflows. By inspecting the Linux kernel loopback drop statistics, you can determine if the host system simply cannot keep up with the volume of telemetry being pushed by the application. Network connection timeouts are another common symptom, frequently indicating that the collector is waiting for an acknowledgement that never arrives due to intermittent packet loss. When diagnosing these timeouts, always check if your host firewall rules have been updated to allow traffic on all necessary egress ports, as silent drops are frequently mistaken for application-level logic errors. Finally, successful troubleshooting requires a structured mindset where we isolate variables one by one. Start by validating the most basic connectivity, ensuring that the machine running the collector can reach the endpoint outside of the collector software itself. If basic network connectivity works, shift your focus to the collector's internal error reporting to identify specific exceptions, like context deadline exceeded. These errors tell us that the collector is attempting to perform an action, such as sending a batch of metrics, but the system cannot complete the operation within the defined timeout period. By systematically verifying your credentials, certificates, configuration syntax, and resource limits, you can resolve the majority of agent errors without reverting to desperate trial and error. Until the next session. Welcome back to our exploration of Splunk Observability. Today, we focus on the critical task of verifying ingestion ports to ensure your telemetry data reaches its destination without obstruction. When we deploy collectors, we assume they are silently listening on the expected ports, but production environments rarely offer such luxuries. In the OpenTelemetry ecosystem, the OTLP receiver is the primary gateway for your spans, metrics, and logs. It standardizes data ingestion by utilizing specific ports for gRPC and HTTP transport protocols. Specifically, the OTLP gRPC endpoint traditionally binds to port 4317, while the OTLP HTTP transport prefers port 4318. If your collector fails to ingest data, the first step is always to verify that these specific ports are indeed open and listening on the host interface. A common oversight involves assuming the service is bound to all network interfaces when it is restricted to the local loopback, which effectively silences the collector from external traffic. To diagnose these transport configurations, we rely on standard Linux network utilities. The S command, or its predecessor netstat, allows us to inspect the state of these sockets effectively. By running istolp, grepi 4317, 4318, we can quickly confirm whether the process has successfully bound to the expected ports. If you see the listening status linked to 127.auth.auth.1, the collector is only accepting local data, meaning remote microservices will be unable to send their telemetry. Conversely, an entry bound to 0.000.donon or the specific instance's public IP address allows for broader network communication. Distinguishing between these binding configurations is essential for troubleshooting connectivity barriers in dense cloud environments where multiple instances share the same network infrastructure. In scenarios where default port conflicts arise, such as when running multiple collector instances on a single dense compute node, we must modify the pipeline configuration. Default port contention signifies that another process has already claimed the socket, leading to immediate service startup failures. Rather than disabling security measures, we can adjust the OTLP receiver settings in the collector configuration file to utilize non-standard ports. After updating these configuration attributes, ensuring the collector restarts properly is non-negotiable. If you find yourself needing to inspect the actual payload traversing these channels, tools like TCP dump become invaluable for verifying that formatted data is indeed hitting the interface. Using a command string like TCP dump anyport 4317.wcapture.pccap allows for deep inspection of the gRPC traffic to confirm the receiver is parsing the binary protocol correctly. Managing complex network paths sometimes requires the use of specialized reverse proxies to mask internal ports or provide an additional layer of load balancing. When traffic passes through a proxy, it is vital to audit that the proxy isn't stripping necessary headers or failing to pass the transport layer signals through to the destination collector. Even if the proxy verifies internally, it might alter the timing or the protocol framing, causing the collector to drop payloads silently. Testing with a direct connection is always the best way to isolate if the issue lies within the collector configuration or the network path leading to it. By systematically removing variables, you can ensure that your ingestion pipeline remains robust and highly available across all your cloud computing nodes. I will see you in the next installment. Welcome to the chapter on metrics architecture concepts, where we will dissect the foundational elements of data ingestion. We shall begin this journey by examining the anatomy of individual data points, which serve as the atomic units of your observability platform. To understand the Splunk Observability Cloud metrics pipeline, you must first perceive a data point not as an abstract signal, but as a structured, serializable object. At its core, every metric is defined by its name, which serves as the primary identifier within the time series database. This string must be unique and descriptive, often following a hierarchical naming convention that allows for efficient filtering and grouping. Accompanying this identifier is the numerical value, which represents the actual observation captured at a specific moment in time. Whether this value is an integer or a floating point number is not merely a syntactic choice, but a decision that impacts how the downstream analytics engine stores and processes the data to maintain precision over extended periods. The temporal aspect of a metric is anchored by a high-precision Onyx epoch timestamp. In the context of streaming telemetry, this timestamp is the absolute arbiter of ordering, allowing the system to place disparate observations into a coherent, chronological sequence. Granularity is essentially the resolution of this timestamp. Variations in how your collectors emit these values can introduce complexities in stream processing, especially when data arrives out of order. Aligning these timestamps is critical, as the observability backend relies on this exact synchronization to perform mathematical rollups and accurate time window aggregations. If your ingestion pipeline is configured with improper timestamp precision, you risk data drops or, worse, significant skew in your real-time analytics. Beyond the name, value, and timestamp, the true expressive power of modern metrics comes from dimensional arrays. These represent the unique metadata context, often structured as nested key-value pairs that describe the origin of a specific signal. Imagine a CPU utilization metric. Without dimensions, you simply know that a server is at 80% load somewhere in your infrastructure. By injecting dimensions like host ID, availability, zone, or container name, you transform a generic data point into a surgically precise diagnostic marker. These metadata pairs are the architectural scaffolding that enables you to pivot across your data, allowing for the high-cardinality analysis that differentiates Splunk observability from legacy monitoring solutions. Serialization formats are the final layer that dictates how these components are encoded for transmission across your network. Whether you are using a standard protocol like OpenTelemetry or a proprietary ingestion format, the serialized payload must correctly encapsulate the metric name, the value, the timestamp, and all associated dimensions into a structured package. Think of this as the grammar of your telemetry. If the schema deviates from the expected format during serialization, the ingestion pipeline will reject the data point, leading to gaps in your data visibility. As you work with collectors and ingesters, visualize each request as this specific packet of information, ensuring that your metadata remains clean and that your value types remain consistent across the lifecycle of your time series data. We will see you in the next lecture. Welcome to our deep dive into the foundational architecture of metric time series within the Splunk infrastructure monitoring environment. In this session, we will examine the precise mechanisms that define unique metric streams and how the platform manages these structures at scale. To understand a metric time series, or MTS, we must first recognize that it is not merely a collection of data points, but a strictly defined identity constructed by the fusion of a metric name and a unique set of dimensions. When an agent reports a telemetry value, the system does not simply store a floating point number in isolation. Instead, it creates a binding between that value and a specific context defined by its metadata. If you collect CPU utilization for a host named Web001 in the US East 1 region, the MTS is the singular, continuous timeline generated by that exact combination. If you were to add a new dimension, such as an application version, the system would immediately treat this as a separate, branching timeline. This is a critical distinction because it dictates how the engine organizes data in the underlying index database. By understanding this boundary, you can begin to predict how your ingestion patterns will influence stored metadata volume and eventual query performance. The structural difference between a single, ephemeral data point and a long-lived time series stream is the primary factor in index memory management. A data point is a snapshot in time, but an MTS is a stateful entity that requires the engine to maintain a reference to its dimension set throughout the data lifecycle. When you perform a query, the backend does not scan a monolithic table. It performs high-speed lookups against specific MTS identifiers. If you have an explosion of dimensions, a condition often referred to as high cardinality, you effectively increase the number of unique timelines the engine must track. This requires significantly more memory to maintain the mapping between metric identifiers and their corresponding storage buckets. Consequently, understanding the cost of these metadata footprints is essential when designing your naming conventions and tag strategies in distributed enterprise environments. Modifying a single dimension key at the point of ingestion has the immediate effect of splitting an existing stream into a distinct time series context. This happens because the system interprets the dimensional signature as a unique key for lookup purposes. For instance, if a service suddenly reports an additional environment tag that wasn't present in previous iterations, the database creates a new slot for this series. The old series does not vanish. It remains as a legacy stream with its own index entry, while the new series begins its own lifecycle. This behavior is intentional, as it preserves the integrity of your trend analytics. Yet it can also lead to index fragmentation if performed haphazardly. Architects must weigh the need for granular reporting against the overhead of generating these new contexts, as excessive streaming forks will inevitably lead to increased latency during dashboard loading or alert evaluation. Navigating dense enterprise telemetry requires an architectural approach that prioritizes efficient index lookups over raw metric retention. The system is designed to handle millions of unique time series, but performance remains contingent upon how clearly your metric identifiers allow for filtered path traversal. By keeping your dimension sets consistent and predictable, you allow the query engine to prune unrelated series branches before executing heavy aggregation functions like rollups or window transformations. When query latency begins to degrade, it is frequently symptoms of the engine struggling to resolve an excessive number of unique MTS matches across your cluster space. Learning to optimize these lookups involves designing your ingestion pipelines to favor stable, low-variance dimensions while offloading high-cardinality metadata to localized logs or tracers. Proper architectural discipline at the ingestion layer is the singular most effective tool for maintaining high-performance observability at scale. I will see you in the next lecture. Welcome back. In this lesson, we will move past the basic architecture of data points to evaluate the specific metric types that serve as the foundation for your observability cloud environment. To effectively monitor a complex system, you must first understand the fundamental behavior of the data you are collecting and how that dictates your choice of metric type. Gauges are essentially the simplest form of observability data, representing a snapshot of a value at a specific point in time. When you track a gauge, you are observing an instantaneous measurement that can fluctuate upward or downward without any intrinsic relationship to previous values. Consider a metric representing the current memory usage of a JVM heap. This value is entirely transient and independent of what the memory usage was 5 minutes ago. Because gauges represent single states, calculating a rate of change on a gauge is often mathematically nonsensical without applying additional temporal transformations. When configuring your monitoring, remember that high polling frequencies on gauges increase your ingestion volume and storage footprint, so you must balance precision against the operational cost of high resolution. Counters serve a different purpose entirely, as they track cumulative event occurrences that are, by design, monotonically increasing. A counter will only ever go up, recording the total number of operations, requests, or errors since the start of a process. The primary challenge when dealing with counters is managing the inevitable reset that occurs when a system reboots or a service restarts, as the total count will drop to zero. Observability. Cloud handles these resets by calculating the difference between successive samples, but you must account for the interval over which you are measuring to derive meaningful rates like requests per second. If you treat a counter as a gauge, you will see a jagged, resetting graph that hides the actual throughput of your service, whereas applying the correct derivative or rate function transforms that raw cumulative value into a smooth, actionable line of velocity. Histograms represent the most sophisticated metric type in your arsenal because they isolate the statistical distribution of data points rather than recording raw values. Instead of tracking every individual request latency, a histogram groups observations into defined buckets based on predefined thresholds. By parsing these bucket counts, tools can reconstruct the distribution, allowing you to identify the P95 or P99 latency values that are invisible to simple averages. Understanding how to map your application requirements to these types is critical. For example, if you need to understand the spread and variability of your response times to detect tail latency issues, a histogram is the only appropriate mathematical model. Conversely, if you force your distribution data into a counter, you lose the ability to perform percentile analysis, effectively blinding yourself to the behavior of the slowest 5% of your user requests. Selecting the correct metric type is not merely a configuration choice, but a direct reflection of how you model the real-world behavior of your system resources. If you are monitoring request rates, a counter provides the accurate, cumulative total that you can then differentiate to find the instantaneous throughput over time. If you decide to monitor the size of a connection pool or the number of active threads, a gauge correctly reflects the current availability of that resource as it expands and contracts. Attempting to use a counter for something like disk temperature or CPU load will yield misleading information, as these are inherently variable measurements that do not represent a total sum. By aligning your metrics with these profiles, you ensure that your dashboards and alerts are mathematically sound and provide an accurate narrative of your infrastructure's health. See you in the next lecture. Hi there. Let's explore data resolution strategies and how they fundamentally shape your observability experience. In this chapter, we will dissect how ingestion intervals and persistent storage mechanisms interact to define the granularity of your metrics. Understanding data resolution requires us to move past the surface-level abstraction of a dashboard and inspect the underlying mechanics of time series storage. At the highest ingestion tier, the Splunk Observability Cloud captures metric data points at their native frequency, which is typically governed by your collection strategy. If you are polling an endpoint every 10 seconds, you are establishing a high-frequency baseline that preserves transient, short-lived spikes. However, storing every single data point indefinitely across vast historical windows is computationally prohibitive for both the storage engine and the query latency. Therefore, the architecture relies on downsampling, where granular data is rolled up into coarser windows as time progresses. This structural transition from raw data points to aggregate buckets is not merely a space-saving measure. It inherently changes the quantitative properties of the data being visualized. When you query a wide historical range, the system must process these aggregated blocks, which explains why a dashboard displaying data from last month performs differently than one showing the last 5 minutes. The concept of resolution directly dictates the maximum historical windows available for specific visualization types, as the system imposes constraints on how much data can be rendered simultaneously. When you visualize a metric, the dashboard component requests data at a resolution that matches the requested time range and pixel density. If you request a 30-day lookback, the system cannot realistically render a raw 1-second resolution signal because it would exceed the client-side rendering capabilities and the network bandwidth limits. Consequently, the visualization interface automatically selects an appropriate resolution, effectively smoothing the data shape. This leads to a critical realization regarding visual fidelity. High-frequency bursts that appear clearly in a 1-hour view are often flattened or averaged out in a 1-month view. While this is an expected byproduct of data management, professionals must remain aware that the visual shape of a trend line is an approximation rather than a strict representation of raw telemetry once you move beyond the most recent time windows. When deciding on polling frequencies, we must account for the distinct characteristics of the underlying infrastructure components. A persistent database node generally exhibits stable performance profiles where a moderate standard resolution polling rate is sufficient to capture operational health trends without placing unnecessary load on the system. In contrast, ephemeral container environments require a more nuanced strategy because these resources are designed to spin up and die in seconds or minutes. If your collection frequency is too slow, you might miss the entire life cycle of a short-lived microservice, resulting in a blind spot in your resource utilization metrics. However, increasing the resolution for ephemeral environments across a massive cluster can lead to an explosion in data volume, which introduces performance overhead. You must balance the need for high-precision visibility for container restarts and performance spikes against the platform's capacity to ingest and store this high-cardinality metadata. Optimizing your polling strategy is essentially an exercise in evaluating the cost versus the value of granular insight. If you find that a metric is being polled every 5 seconds across 5,000 containers, consider whether that granularity is providing actionable intelligence or simply inflating your ingestion costs and processing latency. For many standard metrics, such as a steady-state CPU utilization, sub-minute resolution often provides sufficient diagnostic information without the performance penalty of secondary-level tracking. Conversely, for critical latency signals or business-impacting transaction counters, the added precision is worth the overhead. The goal is to reach a state where your resolution settings serve the requirements of your alert detectors and debugging workflows without placing an undue burden on the platform's ingestion pipeline. By aligning your data resolution with the logical lifecycle of the infrastructure, you ensure that your dashboards remain performant and your historical analysis remains accurate, regardless of the time range selected. I will see you in the next lecture. Welcome. Let us explore the mechanics of data aggregation through rollup functions. This chapter focuses on how we transform granular time series data into meaningful visualizations through controlled statistical compression. In the world of time series analysis, we rarely consume raw data points exactly as they arrive from an instrumented system. When you look at a dashboard spanning several days or weeks, Splunk Observability Cloud cannot possibly render every single raw event individually without crashing your browser or becoming unreadable. Instead, the platform employs rollup functions to compress these raw data points into coarser buckets based on your selected time range. A rollup happens when multiple data points falling within a single time interval are reduced to a single representative value. Choosing the appropriate function, such as sum, minimum, maximum, or average, is not merely about aesthetic preference. It is a fundamental act of mathematical data modeling that dictates the truthfulness of your observability signal. Consider the use case of tracking server request counts versus server CPU utilization. For request counts, applying a sum rollup is mandatory because the total number of requests is an additive property. If you have 10 requests in 1 minute and 12 in the next, the business value is the aggregate sum of 22. If you were to use an average rollup on request counts, you would inadvertently hide the total throughput and report a smoothed-out number that ignores the actual traffic volume. Conversely, when observing CPU saturation, a sum is entirely inappropriate because percentages added together result in nonsensical values exceeding 100%. In this scenario, we must use an average or a maximum rollup to understand the typical operating state of the processor over a specific evaluation window. The choice between these functions directly impacts the shape of your visualization, often introducing artifacts that can mislead an inexperienced operator. For instance, using an average rollup on a highly volatile metric, like memory swap usage or latency spikes, often acts as a low-pass filter that hides critical systemic issues. If your system experiences a sub-second spike in latency that causes a user-facing timeout, an average rollup over a 5-minute window significantly dilutes that signal, potentially making a dangerous event appear benign. Mathematical operators like minimum and maximum functions serve as the bounds for your data, exposing the range of execution rather than just the central tendency. Developing an intuition for whether your data represents an additive quantity or a gauge reading is the primary skill required for choosing the correct rollup strategy inside your data streams. Configuring these parameters explicitly allows you to take control of how the system renders your metrics, ensuring that the visualization maintains integrity across different time resolutions. When the rollup interval is set significantly wider than the reporting frequency of your agents, you are effectively performing lossy compression on your dataset. Understanding this loss allows you to make informed decisions about when to retain high-fidelity raw data and when to accept aggregated snapshots for long-term historical analysis. It is essentially an exercise in balancing technical precision against the cognitive load required to interpret the resulting charts. Always ask yourself whether the mathematical operation being performed on your data reflects the physical reality of the infrastructure you are currently monitoring. See you in the next lecture. Welcome back. In this chapter, we will explore the mechanisms of dimensionality and metadata within Splunk Observability Cloud to effectively categorize your infrastructure data. Understanding how we manage data lifecycle begins with the distinction between static dimensionality and dynamic metadata. When we ingest metrics, we attach key value pairs directly to the data points at the source, which form the static dimensions of our time series. These dimensions define the identity of the metric, such as host names, data centers, or service identifiers, and they are embedded within the ingestion payload itself. Because these are indexed at the point of entry, they remain persistent for the duration of that specific data stream's lifecycle. However, static dimensions are not the only way we classify our infrastructure, as our operational needs often evolve after the initial data ingestion process. This is where dynamic metadata, applied through user interfaces or API endpoints, becomes a powerful tool for extending the context of our metrics without requiring a full redeployment of our agents or modification of our source code. Mastering this distinction ensures that you maintain a clean data model while retaining the flexibility to adapt to changing organizational requirements. Designing a robust taxonomy is arguably the most critical aspect of avoiding key naming collisions and platform-wide indexing friction. When developers and operators independently create dimensions without a centralized naming convention, they often inadvertently introduce high cardinality, which can lead to significant query degradation. You should strive for a consistent structure where key naming follows a predictable pattern, such as using prefixes for specific environments or application layers. For instance, differentiating between an application layer dimension like app version and an infrastructure layer dimension like host ID helps the system optimize index lookups. When keys are structured properly, the query engine can filter subsets of data with much greater efficiency, as the observability platform relies on these keys to partition the underlying data stores. If you neglect these conventions, you will eventually face a scenario where aggregate functions struggle to return results within acceptable timeframes, negatively impacting the performance of your dashboards and detectors. Tag utilization strategies often differentiate a well-optimized observability platform from one that struggles with excessive metadata overhead. We use tags to group components dynamically, which provides a layer of abstraction over the raw dimensional data provided by our agents. While static dimensions are rigid, tags act as a flexible overlay that allows you to categorize infrastructure based on business context or temporary operational needs, such as labeling a cluster for a specific release candidate. You must be careful, however, not to overload the system with overly specific tags that change at high frequencies, as this mirrors the challenges of high cardinality data. Instead, focus on using tags to capture meaningful categories that persist long enough to offer analytical value without inducing unnecessary re-indexing cycles. By balancing structural integrity with flexible tagging, you ensure that your metrics remain both performant and highly relevant to the teams investigating production incidents. In conclusion, managing the metadata lifecycle requires a disciplined approach to both the ingested dimensions and the dynamic properties added post-ingestion. By observing these practices, you establish a reliable foundation for all analytical tasks. I will see you in our next session. Welcome to the chapter on Mastering Built-in Content, where we will learn how to leverage pre-packaged observability assets to gain immediate insights. We are shifting our focus away from manual configuration toward utilizing the robust, factory default tools that Splunk Observability Cloud provides for rapid infrastructure monitoring. When you first land in a fresh instance of Splunk Observability Cloud, it is tempting to start building custom dashboards from scratch, but that often leads to redundant work. The platform includes a comprehensive catalog of out-of-the-box infrastructure monitoring content that covers common cloud service integrations and operating system metrics. By navigating to the default dashboard library, you can instantly provision standardized views for your cloud providers, such as AWS, Google Cloud, or Azure. These layouts are designed as global frameworks, meaning they follow a consistent logical structure intended to reduce cognitive load across your engineering teams. Instead of engineering new visualizations, you should first explore these official assets to see if your monitoring requirements are already addressed by the curated baseline templates. To effectively isolate resources within your environment, you must become comfortable with the global navigation search controls located at the top of the interface. Rather than manually clicking through hierarchy trees, you can use these search inputs to filter by specific dimensions, such as host roles, regions, or custom environment tags. Once you trigger a search, the platform dynamically updates the infrastructure landing pages, which serve as the primary entry point for your operational visibility. These landing pages provide a high-level summary health bar that acts as your first line of defense during an incident. This summary component aggregates state information from all monitored entities, allowing you to instantly assess whether your infrastructure is healthy or if you need to drill deeper into specific problem areas. Efficiency in monitoring often comes down to the speed with which you can transition between high-level macro maps and granular entity views. When you interact with a summary health bar or a specific resource list, you are essentially initiating a contextual pivot that maintains your focus on a particular subset of signal data. By clicking on a specific entity, such as an individual cloud instance or a container, you move from an organizational level perspective to a localized entity view that includes specific time series charts for that discrete resource. This fluid navigation model is a core strength of the platform, as it eliminates the need to manually reconfigure your scope settings every time you switch contexts. You are navigating through pre-configured, curated environments that have been optimized to display the most critical performance metrics for each specific infrastructure type. Establishing immediate baseline visibility without custom engineering is a professional prerequisite for scaling your observability practice. Many practitioners lose significant time by attempting to solve visualization challenges using bespoke queries when standard, industry-proven dashboards are already available. The built-in content is not merely a collection of simple charts. It represents deeply integrated intelligence regarding how typical cloud services interact, including default threshold approximations and performance indicators. By adopting these standardized views, you ensure that everyone on your team is looking at the same metrics, using the same terminology, and applying the same health conventions. This consistency is the foundation upon which you can build more complex, custom observability strategies once the basic infrastructural visibility is secured and understood. See you in the next lecture. Welcome back, and let us begin examining how to extract operational insights from default charts. We will focus on the mechanics of out-of-the-box visualizations, SignalFlow logic, and standard metadata filtering. When you first open a dashboard in Splunk Observability Cloud, you are presented with pre-configured visualizations that rely on existing analytical transformations. These default charts are designed to provide an immediate assessment of your system's health without requiring manual intervention or complex configuration. However, relying purely on surface-level observation often leads to misinterpretation if you do not understand the underlying mechanics of how these metrics are rendered. Every chart you encounter, whether it displays CPU utilization or request latency, is backed by hidden SignalFlow logic. This logic defines the data points being polled, the rollup operations being applied, and the statistical aggregations that govern the resulting visual display. By learning to recognize these invisible processes, you move from simply reading a graph to understanding the architecture of the metrics it represents. This transition is essential for any practitioner aiming to move beyond basic monitoring into true observability and root cause analysis. One of the most critical aspects of these pre-configured charts is the concept of implicit rollup and native sampling resolution. When your data sources emit thousands of metrics, the platform cannot plot every single raw data point without overwhelming your browser or blurring the visual signal. Instead, the chart uses automatic rollup selections, such as averaging or taking the maximum value over specific time intervals that align with your selected zoom level. If your time range is wide, the resolution is naturally lower to maintain performance. Recognizing this means acknowledging that you are looking at a summarized view, not necessarily the absolute peak or valley of an individual request. When you see visual cues that highlight system anomalies, such as color changes or shaded regions in the chart, you must understand that these are driven by threshold-based definitions already baked into the chart settings. Knowing how these thresholds trigger ensures you do not mistake a localized normalization artifact for a genuine infrastructure failure. Multi-axis configurations often present a significant friction point for new users when multiple metrics of different types are plotted on a single view. You may see a bar chart representing request counts alongside a line plot for latency, both sharing a time axis but using disparate y-axis scales. The platform handles this by normalizing these units, but the responsibility to correctly interpret these distinct scale ranges remains with you. Furthermore, these charts apply structural metadata filters automatically, which are designed to present localized, noise-free infrastructure performance visualizations. These filters ensure that, for instance, a cluster-level graph does not accidentally aggregate metrics from development, staging, and production environments together. By understanding the metadata tags and label propagation that influence these selections, you can verify if a specific chart is truly showing the data segment you need. This structural metadata is the backbone of localized reporting across standardized workloads across your cloud environment. Time-shifted comparison charts are another staple of out-of-the-box content, serving as a powerful tool for trend analysis. These charts function by overlaying current data with historical snapshots, usually from an hour, a day, or a week ago. When you analyze these displays, remember that they are executing multiple SignalFlow operations in parallel to fetch both the current time window and the historical counterpart. If the data appears fragmented or disjointed, it is often due to the misalignment of data ingestion windows between the two periods. Evaluating these views requires a keen eye for seasonality in your metrics, as the visual cues are intended to highlight deviations from established baselines rather than just individual spikes. Mastering these interpretive techniques allows you to ignore the superficial noise of temporary jitter and focus on identifying patterns that indicate systemic shifts in infrastructure performance over time. Understanding the automated legend generation is the final piece of this puzzle for interpreting standard visual displays. The legend is not just a label list. It is a direct mapping of the dimensions currently powering the graph output. If you notice a legend entry that appears truncated or ambiguous, it is usually because the metric carries high-cardinality metadata that the chart has simplified for readability. You can often hover over these elements to reveal the full tag set, which helps in identifying exact source hosts or containers contributing to the visualized values. When you take the time to dissect the relationship between the legend and the underlying signal flow, you gain a clearer picture of which infrastructure components are influencing your dashboard metrics. This clarity enables you to trust the data presented in default views and empowers you to iterate on them when more specific diagnostic visibility is required. I look forward to discussing the next topic when you are ready. Welcome to this chapter on built-in content mastery, where we will examine how to effectively consume and manage alerting data. In this specific session, we will focus on the mechanics of subscribing to alerts so you can stay informed about your infrastructure. Subscribing to alerts within the Splunk Observability Cloud platform is fundamentally about closing the loop between a system detector and the human operators responsible for the underlying services. While detectors evaluate incoming metric streams against defined thresholds or anomaly patterns, they do not inherently know who needs to be notified when a state transition occurs. By creating a subscription, you establish a direct logical link between the detector output and specific communication channels. This process requires a clear understanding of the difference between global notifications, which often broadcast events to broad administrative teams, and localized target routing rules that pinpoint specific engineers. When you configure these subscriptions, you are effectively defining the dispatch strategy for your organization. Proper orchestration of these streams ensures that information is not just generated, but actively delivered to the appropriate recipients. When configuring these subscriptions, you must first determine the destination for your notifications. The system provides several built-in mechanisms, including direct email delivery, webhooks for integration with external automation tools, and native integrations with collaboration platforms like Slack or Microsoft Teams. Selecting an appropriate messaging format is critical because the signal-to-noise ratio matters significantly. Sending a high-frequency alert into a general team chat can lead to alert fatigue, while sending a critical heartbeat failure to a secondary email folder ensures the issue remains unresolved. You define these settings within the subscription profile, where you can also map the alerts to your organizational escalation matrix. This mapping is vital for mission-critical infrastructure, as it ensures that if a primary engineer does not acknowledge an alert within a set timeframe, the system automatically routes that event to a secondary or tertiary contact. Personalized subscription properties allow users to tailor their experience based on their specific roles. You can link your individual user account to specific high-priority alerting streams, or you can attach entire workspaces to ensure that all members of an SRE team receive the same set of notifications for a cluster. This distinction is important when you consider that global platform notifications are often managed at the organization level, while individual subscription rules offer granular control over exactly what reaches an individual's personal notification queue. By managing these rules, you control the lifecycle of the alert notification itself. It is a configuration-based approach to incident response that leverages the built-in system detectors to do the heavy lifting of data analysis, while your subscription rules handle the human-centric component of alerting orchestration. Configuration involves navigating to the alert settings and selecting the desired notification channel. You must carefully define the routing logic, especially if you're working within a complex environment where multiple services share the same infrastructure. If you fail to route these events properly, critical events might be ignored or lost within a flood of non-actionable data. Always ensure that the selected transport mechanism for your subscription is supported by your team's current incident response tooling. For instance, using a webhook to trigger a custom remediation script is a common pattern for managing transient cloud infrastructure issues, provided those scripts are designed to account for the incoming payload structure. By thoughtfully structuring these subscriptions, you ensure that engineering teams receive the right information at the precise moment it is required to prevent a service degradation. See you in the next lecture. Welcome to our deep dive into Kubernetes Navigator operations. This chapter will equip you with the precise skills required to navigate complex microservices clusters using Splunk Observability Cloud's curated Kubernetes tools. Mastering these navigation patterns is essential for any engineer tasked with maintaining high availability in containerized environments. You will learn how to transition seamlessly from a high-level cluster summary down to the individual container level to resolve infrastructure bottlenecks. By following this structured approach, you will significantly reduce your mean time to resolution during critical production incidents. Now, we turn our attention to the tactical operation of the Kubernetes Navigator, a tool designed specifically to demystify the multi-level hierarchical topology of your clusters. When you arrive at the Navigator view, the primary objective is to maintain a mental model of your cluster structure while simultaneously scanning for anomalies in resource utilization. Unlike generic dashboarding tools, the Navigator provides a curated representation that mirrors how your workloads actually interact with physical infrastructure. You start at the global cluster level where you can observe aggregate health metrics, but the real power lies in the ability to drill down into specific namespaces. By creating these logical delineations, you can isolate problematic services that might be affecting a broader set of dependencies. The interface allows you to transition your perspective from the cluster to the worker node, effectively filtering the noise of healthy components while focusing your aperture on failing runtime instances. Once you have isolated a suspicious worker node, the analysis shifts toward auditing the relationship between container resource limits and actual telemetry data. You must inspect the container runtime environment to identify if a service is hitting its enforced CPU or memory ceilings, which often manifests as persistent container restarts. In the Navigator, you can correlate physical node saturation with these runtime failures by observing the impact of noisy neighbors on the specific container in question. Pay close attention to CPU throttling indicators, as these are often leading signals of performance degradation that precede complete application crashes. When a pod experiences throttling, it signifies that the kernel has enforced a limit, preventing the container from accessing its allocated time slice. This is where the visual map interface proves its worth, as it allows you to see how container bottlenecks create a ripple effect through your clustered application service dependencies. Using the Navigator effectively requires a disciplined approach to identifying the root cause of service latency, which often involves a transition from the physical to the logical layer. You should begin your triage by examining the node-level metrics to ensure that the underlying host is not experiencing resource exhaustion. If the node displays high saturation levels, even if the node itself is not crashing, it might be starving the pods of necessary compute resources. Once you rule out the host, look at the container resource limits versus their usage patterns. This comparison is fundamental for identifying misconfigured liveness or readiness probes that might contribute to unnecessary restart cycles. The dynamic map interface is particularly useful for discovering structural dependencies where a bottleneck in a single upstream container halts traffic flowing to downstream microservices. Effectively using these indicators creates a feedback loop where you verify, isolate, and remediate systemic issues within an integrated visual context. We will continue our exploration of infrastructure monitoring in the next lecture. Welcome to this exploration of the Cluster Analyzer, where we transform complex Kubernetes signals into actionable infrastructure insights. We will examine how automated diagnostics cut through the noise of distributed systems to pinpoint root causes. In any reasonably complex Kubernetes deployment, the sheer volume of telemetry data can become an obstacle to finding the truth. When a cluster experiences performance degradation, manually checking nodes or pods is often insufficient because the failure might be systemic or hidden deep within the scheduling logic. The cluster analyzer serves as an automated diagnostic engine that monitors your infrastructure for mathematical outliers and configuration anomalies. It effectively acts as a specialized layer of observability that abstracts away the manual labor of mapping resource consumption against established operational models. By leveraging machine learning analytics, this tool processes statistical summaries to highlight where your environment deviates from its historical performance baseline. Understanding why a specific node is over-provisioned or why a set of pods is failing to scale requires more than just raw logs. It requires a context-aware analysis of the entire overlay network plane. The engine identifies these patterns by constantly running diagnostic routines that compare current workload distributions against expected capacity allocations. This approach allows you to shift your focus from interpreting individual events to understanding the aggregate behavior of your clusters. When we interact with the cluster analyzer, our primary goal is to interpret the statistical outlier summaries that indicate bottlenecks or deployment failures. These summaries are not merely collections of error codes, but rather mathematical representations of how your containers are behaving compared to the rest of the ecosystem. Scheduling bottlenecks often present themselves as disparities between node capacity and the aggregate resource requests of the pods assigned to them. Without automated intervention, identifying these imbalances remains a tedious task of comparing node-level metrics across large datasets. The analyzer simplifies this by mapping consumption profiles and highlighting zones where resource saturation is impacting latency or throughput. If a network connectivity error occurs across the overlay, the tool correlates these telemetry signals to show if the issue is confined to a specific service or if it impacts the broader cluster communication channels. By mapping these signals, you gain a perspective on systemic performance degradation that would be nearly impossible to derive from static dashboards alone. Effective use of these automated insights involves trusting the underlying diagnostics while keeping a close eye on the mathematical assumptions. You should view the output provided by the cluster analyzer as a set of hypotheses that require validation against your specific infrastructure topology. For instance, when the system flags a container configuration anomaly, it is usually pointing to a deviation in resource limits or an improper interaction with the scheduler. You must consider whether these anomalies correlate with recent deployment changes or if they indicate a latent architectural flaw that has been exacerbated by increased traffic load. By grounding our observations in these historical operational models, we can distinguish between transient spikes and genuine degradation vectors. The goal is to move beyond simple troubleshooting toward a proactive state where you can identify and correct imbalances before they manifest as service-level objective violations. Every piece of telemetry processed by the engine informs the next diagnostic cycle, allowing you to refine your operations as your environment scales. I look forward to our next session together. Welcome back. In this session, we will examine the built-in Kubernetes dashboards provided by the Observability Cloud to monitor and troubleshoot complex containerized environments effectively. When managing Kubernetes clusters at scale, the primary challenge is not the lack of data, but the cognitive load required to synthesize it during an incident. Built-in dashboards provide a curated view of the control plane and data plane health, abstracting away the complexity of raw metric queries. You will find that these dashboards are segmented into logical areas, such as cluster overview, node-level health, and pod-specific resource utilization. By leveraging these pre-built visualizations, we can immediately identify common failure modes, such as memory pressure on specific nodes or throttling of CPU resources for critical workloads. The beauty of these dashboards lies in their consistency, as they utilize standardized metric naming conventions that apply across different Kubernetes providers. Understanding how to parse these standard charts allows an operator to look for meaningful trends rather than trying to interpret isolated spikes in traffic or resource consumption. To start, consider the kubelet operational health charts, which serve as the heartbeat of your worker nodes. These visualizations monitor the registration and heartbeat status, ensuring that the control plane maintains a healthy connection to the nodes. If you observe latency within the API server request charts, you are likely looking at issues related to request throughput or controller inefficiencies that might be causing a backlog in cluster state updates. Furthermore, these dashboards excel at auditing container memory pressures, providing clear visibility into which specific pods are nearing their memory limits or hitting out-of-memory kill events. When dealing with persistent volume capacity limits, the built-in views highlight disk saturation before it leads to cascading application failures. This proactive stance is essential when managing multi-region environments where manual tracking of thousands of persistent volumes would be practically impossible. Efficiency and resource allocation is another pillar of these dashboards, specifically when auditing containerized workloads against defined resource request boundaries. When a pod consistently utilizes only a fraction of its requested resources, or conversely, hits its limits, you can easily correlate this behavior using the provided time series views. Reviewing core DNS lookup failure rates is equally vital, as these visualizations often act as the first indicator of network layer drops or service discovery misconfigurations within your namespace. By setting operational filters, you can narrow your focus to specific deployments that may be misbehaving, filtering out the noise from the rest of your production cluster. These filters are not mere cosmetic wrappers, but powerful tools that allow you to isolate anomalies based on dimensions such as namespace, service name, or node region. Utilizing these tools effectively requires a deep understanding of standard Kubernetes metrics terminology, which the platform maps automatically upon ingestion. The true strength of the platform resides in its ability to present these metrics with enough context to make informed decisions without building custom queries from scratch. Whether you are investigating why a specific set of containers is underperforming or evaluating if your cluster scaling policies are aligned with current traffic patterns, the pre-built dashboards serve as the source of truth. By reviewing the latency and error rate distributions, you gain insight into the network reliability of your inter-service communications. When you find an issue, you can immediately pivot from a high-level cluster view to the specific problematic pod and analyze its local metrics. This streamlined workflow reduces mean time to resolution by removing the overhead of dashboard configuration during the heat of an emergency. Master these built-in views, and you will find that a significant portion of your daily operational tasks becomes a matter of interpreting clear, actionable signals. I look forward to our next discussion on effective metric visualization. Welcome to our exploration of Metric Finder search patterns. where we will refine how you navigate complex telemetry environments. In this chapter, we will master the syntax and intuitive search capabilities of the Metric Finder interface to isolate specific data points efficiently. When we interact with the Metric Finder, we are essentially performing a structured query against a sprawling catalog that may contain millions of distinct metric definitions. To make sense of this noise, move beyond simple keyword searches and embrace the power of dimensional metadata filtering. Think of these dimensions as the attributes that define the context of your data: host names, environments, services, or resource identifiers. By applying an exact match syntax, such as specifying key value pairs like environment, production, or service, auth API, you eliminate the ambiguity that typically plagues large-scale observability setups. The interface provides autocomplete suggestions that, while convenient, should serve as a secondary tool to the precise queries you construct. If you know the exact structure of your metric name, lead with the most restrictive dimension to prune the result tree immediately before you even begin to inspect individual time series. Boolean logic is your primary instrument for carving out relevant subsets from the background telemetry noise. You can combine multiple filters using logical operators, which allows you to define complex conditions that accurately represent the state of a specific service. For instance, if you're debugging a latency issue in a Canary deployment, you might craft a query that merges host pool, Canary, with metric name, Ostic latency. The use of wildcard operators here is not merely about finding approximate matches, but about efficiently grouping metrics that follow a naming convention or a common schema. When you encounter orphan metric names, those that appear in your catalog but demonstrate no active data points, you should leverage non-existence filters to effectively hide them from your search results. Keeping your view clean of stale data is not just an aesthetic choice. It reduces cognitive load when you are responding to an actual production incident. The efficiency of your workflow is dictated by how quickly you can pivot from curiosity to resolution. Once you have constructed a search pattern that successfully isolated the signals you need, you should habitually save these as reusable search profiles. Reusing these profiles prevents the repetitive effort of typing complex Boolean strings and ensures consistency across your team's monitoring efforts. Consider how these saved views function as bookmarks into your infrastructure, bridging the gap between a raw stream of data and a diagnostic chart. As your telemetry catalog grows, these search patterns shift from being a mere convenience to a fundamental requirement for maintaining visibility. By mastering these patterns, you stop fighting with the search interface and start leveraging it to navigate even the most complex enterprise architectures with confidence. I will see you in the next lecture. Welcome back. Today we examine the fundamental mechanics of the chart builder, the primary interface for transforming raw metric streams into meaningful visual representations. When we approach the chart builder, we are essentially moving from the static world of pre-built dashboards into the realm of bespoke data exploration. The interface is designed to bridge the gap between underlying metric telemetry and human-readable patterns. You start by identifying the specific signal lines that represent the health or performance of your services. By selecting a metric target, you define the core data source, but the real power lies in how you constrain that data. Through the application of localized multidimensional filters, you ensure that the chart only displays relevant information, preventing the noise of high-cardinality environments from obscuring your view. If you ignore these filters, you risk creating a visualization that is too dense to interpret, essentially rendering the metric useless for operational decision-making. In practice, a single canvas rarely tells the whole story, which is why the tool allows for the seamless addition of multiple independent signal plots. You must be methodical when mapping these signals to specific data source types, such as infrastructure metrics versus custom application events. By bringing different signals onto one plot, you can visually correlate events that might otherwise seem disconnected. For example, overlaying CPU utilization with request latency often reveals a causal relationship that justifies a specific scaling policy. It is crucial to remember that each added plot retains its own configuration, allowing for granular control over how every signal contributes to the final narrative. This layering capability is what distinguishes a mere chart from a diagnostic tool capable of guiding incident response. Users frequently encounter issues with default resolution settings, which are often generalized to provide a balanced view across varying time ranges. However, during an active investigation, you might need higher fidelity data than the default sampling rate provides. Within the interface, you can override these defaults by manually adjusting the resolution settings, which forces the system to pull more granular data points. While this provides clarity, you must remain mindful that higher resolution over long time windows increases the computation cost and potentially slows down the rendering of the browser view. Always select an evaluation time window that aligns with the context of your investigation. If you are troubleshooting a transient spike, a narrow window is superior to a wide one. One of the most powerful features of this interface is the ability to perform algebraic plot manipulation without needing to write complex code. The system provides a set of UI-driven transformations that allow you to aggregate or calculate ratios between different signals on the fly. Suppose you have two separate signals representing successful requests and total requests. You can configure an arithmetic rule directly in the builder to visualize the actual error rate as a percentage. These manipulations happen at the query level, ensuring that the visualization always reflects the most current state of the system based on live data processing. Because these transformations are applied downstream, your underlying raw telemetry remains untouched, allowing you to experiment with different analytical views safely. Ultimately, mastering the chart builder is about understanding how to translate operational requirements into a visual format that can be easily understood by your team. Whether you are creating a dashboard for daily monitoring or a specific view for a root cause analysis, the process remains consistent. You identify the target, filter for relevance, adjust the resolution for precision, and layer plots for context. By relying on these mechanisms, rather than trying to force a generic view to fit an edge case scenario, you produce more resilient and actionable dashboards. Keep these principles in mind as you begin constructing your own custom visualizations throughout the platform. I will see you in the next lecture. Welcome back. In this chapter, we will master the art of assembling and managing bespoke enterprise dashboards to establish unified operational visibility. Building a custom dashboard is the primary way to transition from reactive monitoring to proactive operational oversight in Splunk Observability Cloud. When you initiate an empty dashboard canvas, you are effectively creating a blank control plane where you can aggregate disparate telemetry signals into a meaningful narrative. You start by selecting the Create New Dashboard option, which provides you with a clean slate to curate metrics from your technical services. Designing these interfaces acts as a mediator mechanism between raw machine data and the human stakeholders who need to act on that data. By instantiating visualization cells, you define specific windows through which you can view your system's health. Good dashboard design is an exercise in managing cognitive load. You want just enough information to identify a problem, but not so much that you induce alert fatigue or distraction. Once your cells exist, you use the drag and drop mechanics of the layout grid to arrange them in a hierarchy that reflects your business priorities. I find that aligning charts according to the flow of a transaction, such as from the user interface down to the backend database, makes troubleshooting significantly more intuitive for the entire engineering team. Once your layout is optimized, the real power comes from configuring global dashboard-level filters to manage your data dimensionality. Instead of hard-coding every variable into every single chart, you can set up global overrides that affect every child chart on the board simultaneously. This allows a user to select a specific environment host or service tag once and have the entire dashboard update to reflect that specific scope. This design pattern enforces the principle of don't repeat yourself, as you avoid the tedious task of manually configuring filters for every individual widget. If you discover that a particular set of visualizations is useful for a different service, use the cloning tool to duplicate those assets across environments. This saves precious time, ensures consistency across your technical services, and keeps your operational standards high. However, with the ability to create and copy dashboards comes the need for robust access control mechanisms. You have the ability to manage permission configurations to restrict unauthorized edits, ensuring that your carefully crafted layout remains stable and reliable. By publishing these final dashboards to a shared organizational workspace, you provide every team with a single source of truth, effectively breaking down the silos that often plague complex distributed systems. See you in the next lecture. Welcome back. In this session, we will examine the mechanisms for organizing and securing your observability workspace through effective dashboard group administration. When we scale an observability platform across an enterprise, the primary challenge transitions from simple metric visualization to information architecture. A flat list of dashboards quickly becomes unsustainable, leading to configuration sprawl where users struggle to locate relevant signals. Dashboard groups serve as our primary container for logical hierarchy, allowing us to align visibility with functional, organizational teams. By creating nested structures based on domains such as backend services, database clusters, or front-end interfaces, we establish a clean navigation taxonomy. This structure is not merely cosmetic, it is the foundation for enforcing security boundaries. When you link a dashboard group to specific teams, you define a clear scope of responsibility and access, ensuring that developers and operators interact only with the data pertinent to their workflows. Security within Splunk Observability Cloud relies heavily on granular write access policies applied at the group level. Rather than managing individual dashboard permissions, which is an error-prone and tedious task, we configure policies that govern entire collections. This approach allows us to delegate management authority to specific team leads while maintaining central administrative oversight. If we need to move a dashboard from one group to another, the system handles the transition through a simple interface. Yet the underlying permission inheritance remains intact. Auditing access history is equally critical here. By enforcing consistent governance standards, we can trace who made changes to a dashboard group and when those modifications occurred. This audit trail is essential for compliance in regulated environments where every configuration change must be accounted for and verified. To prevent the common pitfall of configuration sprawl, we must enforce rigorous naming conventions across all group levels. A lack of structure leads to duplicate dashboards and conflicting instructions, which ultimately undermines the utility of the observability platform. A standardized naming strategy should encompass the domain, the environment, and perhaps the primary stakeholder involved. Furthermore, setting group-level landing parameters allows us to tailor the user experience by directing traffic to the most relevant metrics upon group entry. This ensures that when a team member accesses their respective group, they are immediately greeted by a curated view of their domain rather than a daunting, unorganized workspace. By investing time in these structural details, we transform an unmanageable collection of data points into a cohesive, intentional monitoring environment. Managing large-scale enterprise workspaces requires a proactive approach to taxonomy governance. It is far easier to design an extensible hierarchy at the beginning than it is to reclassify hundreds of existing dashboards later in the lifecycle. As you define your groups, consider the intersection of your organizational charts and your technical architecture. When your monitoring structure mirrors your team structure, communication improves and incident response times typically decrease. We should periodically review these groupings to ensure they still reflect the current state of our infrastructure. By prioritizing these administrative patterns as highly as our technical instrumentation, we ensure that our observability platform remains a valuable asset for the entire organization rather than a source of informational noise. See you in the next lesson. Welcome back. We are now entering a section dedicated to the visual representation of data, where we will learn how to select the right chart types to make our metric signals truly readable. Choosing the correct visualization is rarely about aesthetics and almost always about reducing the cognitive load required to interpret a system's state. When we deal with metrics, we are essentially trying to answer specific operational questions, and the chosen chart type must act as an interface between raw data and human decision-making. A time series line graph is often the default choice, but it carries inherent dangers when the data density becomes too high. Once you attempt to plot more than a handful of concurrent signals, you encounter the spaghetti effect, where individual trends become indistinguishable, effectively rendering the chart useless for identifying specific outliers. In these cases, opting for a heat map becomes the superior engineering decision because it maps the density of data points across a spectrum, allowing an operator to spot structural anomalies across thousands of hosts without requiring individual line identification. Single value indicators serve a completely different purpose as they are designed to provide immediate status awareness rather than trend analysis. These components are most effective when coupled with color-mapped threshold rules that translate numerical values into actionable health states like warning or critical. By configuring these thresholds, you allow the observer to bypass the need to evaluate if a number is high or low, because the color shift provides that semantic layer automatically. Use these sparingly for key performance indicators, such as total system load or active error counts, where the current state is the only information an engineer needs to see in that moment. If you find yourself needing to display these values alongside long-term trends, consider keeping them as standalone summary cards at the top of your dashboard rather than overloading more complex chart canvases. When we shift our focus to list charts, we are usually looking to identify specific resource consumers within an aggregate set. Lists are indispensable when the identity of the source, such as a host name or a container ID, is just as important as the metric value itself. For example, when you monitor memory utilization across a cluster, a list chart configured to display the top 10 consumers provides an immediate lead for investigation efforts. This is far more efficient than a graph in this specific context because the list structure presents sorted metadata alongside quantitative metrics, facilitating a direct transition from identifying the source to taking remediation action. Always ensure these lists are constrained to a relevant top-end configuration to prevent the dashboard from becoming cluttered with marginally important information. Advanced users often face scenarios where a single visualization type fails to tell the complete operational story. This is where plot overrides become a critical feature in our toolkit, allowing us to combine different formats within a single composite analytics canvas. Imagine a scenario where you have a primary time series line measuring request volume, but you also need to overlay distinct event markers or a secondary threshold-based limit. By applying plot overrides, you can change the display properties for individual metrics, turning some markers into bar charts while others remain lines. This layering capability provides context, such as visualizing a code deployment event as a vertical line against a background of latency spikes. Mastery of these overrides allows you to create dense, information-rich views that don't sacrifice clarity, enabling us to correlate multiple performance signals within a unified visualization. Selecting the right container for your data requires a disciplined understanding of your operational goals. Always evaluate if your data is meant for trend detection, individual unit status, or resource ranking before committing to a visual format. By consciously applying these constraints, you move beyond mere dashboarding and into the realm of meaningful observability. Until the next lecture. Welcome back. In this lecture, we will explore the powerful world of analytic transformations within the Splunk Observability Cloud platform. When we visualize metric data, the raw signal is often not enough to provide immediate operational value. Sometimes a raw stream of data points can be noisy, or it may exist in units that are difficult for human stakeholders to interpret quickly. Analytic transformations allow us to inject complex processing functions directly into our data signals to execute real-time modifications. Instead of viewing raw bytes, we can apply scaling transformations to convert those values into readable gigabytes or terabytes, which makes infrastructure capacity planning much more intuitive. Furthermore, we can implement time window aggregations, such as moving averages, to smooth out short-term fluctuations and identify genuine trends. This capability ensures that our dashboards represent meaningful insights rather than the jittery noise that often accompanies high-frequency metrics. By mastering these transformations, you bridge the gap between raw telemetry collection and actionable observability. Beyond simple scaling, we often need to understand the behavior of dynamic groups rather than individual data points. Spatial aggregations allow us to calculate statistical means or sums across entire clusters of host infrastructure in real time. This is particularly useful when you need to observe the aggregate resource consumption of a microservice deployment, regardless of which specific container instances are active at the moment. As we apply these transformations, we also need to consider the mathematical order of operations, especially when signals are processed in cascading streams. Incorrectly sequencing these functions can lead to flawed analytical outputs, such as calculating a sum before performing a unit conversion, which propagates errors downstream. Proper calculation ordering ensures that the final result reflects the physical reality of the environment. Consequently, we must design our analytical pipelines with a clear understanding of data flow and state management. One of the most critical aspects of advanced observability involves detecting changes in the rate of resource consumption. By configuring rate of change functions, we can effectively identify accelerating patterns in CPU or memory usage before they cross a critical threshold. This proactive approach to anomaly detection is significantly more valuable than waiting for an alert to trigger based on a static upper bound. When you combine these rate-based functions with time window smoothing, you create a robust mechanism for distinguishing between temporary usage spikes and sustainable growth trends. These advanced metrics enable engineers to make data-driven infrastructure scaling decisions. As you refine your charts, remember that the most effective visualizations hide unnecessary complexity while exposing the underlying signals that matter most. Through these transformations, Splunk Observability Cloud provides a sophisticated mathematical engine that operates alongside your telemetry data. See you in the next session. Hi there. Let's explore how to bridge the gap between visual monitoring and automated alerting by deriving detectors directly from your custom charts. In this chapter, we focus on the efficiency of translating visual insights into automated operational logic. You will learn how to transition from simply observing data trends to enforcing defined thresholds through the detector creation wizard. By mastering these workflows, you reduce the time required to configure robust alerting systems from scratch. We will walk through the mechanics of inheriting filter properties and dimension scopes to ensure your detectors remain consistent with your existing dashboards. Efficient alert management is the hallmark of a senior observer, and this module is crafted to sharpen that specific skill set. When you identify a trend in a custom chart that warrants an automated response, you do not need to manually reconstruct the underlying logic in a separate interface. The Splunk Observability Cloud interface allows you to instantiate a detector directly from an existing chart cell. By selecting the option to create a detector from a chart, the system automatically parses the underlying SignalFlow code stream that drives that specific visualization. This process captures the exact metric name, the applied transformations, and the specific dimension filters that you have already validated. Inheriting these properties ensures that the detector evaluates the same stream of data you have been observing visually, which minimizes configuration drift and potential errors in logic. The detector creation wizard then walks you through the transition from a chart-based representation to a persistent alerting path. Once the wizard pulls the SignalFlow logic into the editor, it creates an immediate bridge between your visual data shape and the background evaluation engine. You are presented with a configuration interface where you can define the specific thresholds that trigger an alert event. Because the dimension scopes are already inherited, you ensure that the alerting logic aligns perfectly with the data granularity seen in your dashboard. This fidelity is critical because it prevents the common mismatch where a dashboard shows one behavior while an alert engine evaluates a slightly different signal subset. During this process, validation becomes an essential phase to confirm that your intent matches the system's execution. The UI provides a real-time view of how the detector interprets your chosen metric over time, displaying historical trigger points based on the current threshold settings. By checking this preview, you can adjust the sensitivity of the detector before saving it to your production monitoring path. This step-by-step validation allows you to see how your conditions, such as a static threshold or a more complex rate of change, respond to the actual data volume. It is essentially translating your visual intuition into concrete rules that the system can reliably monitor on your behalf without human intervention. One aspect that requires careful attention is the separation between your dashboard monitoring and your alerting logic. After the detector is created, it functions as a standalone entity in the backend, independent of the chart from which it originated. If you decide to modify the filters or groupings on your dashboard later, those changes will not propagate to the detector unless you explicitly synchronize them. This architectural choice is intentional. It protects your critical production alerts from being unintentionally altered by someone who is merely adjusting a chart for a dashboard presentation. Maintaining this clear separation ensures that your alerting system remains stable and predictable, regardless of how your analytical displays evolve over time. Effective operational practice dictates that you treat your detector construction as a formal extension of your visualization strategy. By keeping your monitoring logic tied to these predefined source expressions, you maintain a source of truth that is consistent across both your human-readable dashboards and your automated machine-driven alerts. As your infrastructure grows in scale, This repeatability becomes the primary method for ensuring that all critical data points are being tracked with appropriate sensitivity. Whether you are scaling from a single service to a cluster-wide implementation, using existing charts as templates allows you to codify your best practices into the platform itself. See you in the next session. Welcome to the chapter on Advanced Detector Management Strategies. We will discuss how to safely duplicate, modify, and expand existing alerting configurations to suit changing infrastructure requirements. In the Splunk Observability Cloud platform, manually recreating complex detectors is rarely the most efficient path forward. Instead, you should master the art of cloning existing, battle-tested alert rules to serve as functional templates for new components. When you clone a detector, you effectively capture its underlying signal flow logic, threshold settings, and notification routing without the overhead of rebuilding those definitions from scratch. The fundamental goal here is to maintain consistency across your observability suite while minimizing the human error that often creeps into manual configuration. By taking a successful production alert as your baseline, you ensure that the core logic, which has already been vetted for accuracy and performance, is preserved in your new iteration. This practice is particularly valuable when you are expanding monitoring to newly deployed software modules that share similar telemetry characteristics with your existing architecture. Once a detector is cloned, the immediate next step involves swapping the base metric identifiers to point toward the new target components. You must be methodical when replacing metric names, as failing to update these underlying signals will result in your new detector monitoring the health of the wrong service entirely. After adjusting the signal targets, the next logical improvement is to expand the dimensional evaluation scope. Splunk allows you to add nested, multi-signal Boolean parameters, which refine the detector's sensitivity by correlating data across multiple metadata dimensions. Think of this as adding context to a broad alert. A high-latency signal is significant on its own, but when combined with a specific availability zone or container tag as a requirement for the alert to trigger, your signal-to-noise ratio improves dramatically. These adjustments represent the intersection of system knowledge and observability strategy. Managing thresholds is another critical aspect of customizing a clone detector. Depending on the nature of the service, you might need to shift from a rigid static threshold to a dynamic range that adjusts based on historical norms. You should carefully review the pre-configured warning and critical levels, as valid operation parameters for one workload type or environment often prove unsuitable for another. When you modify these values, remember that you are effectively redefining what constitutes a performance degradation for that specific software component. Before finalizing your changes, it is essential to utilize the historical data playground provided in the interface. This feature allows you to simulate how your modified detector would have behaved over the past few hours or days, effectively acting as a unit test for your alerting logic. Finally, you must update the notification routing vectors to ensure that alerts reach the appropriate team. A clone detector will often retain the notification channels of its ancestor, which can lead to irrelevant alerts triggering on the wrong engineering Slack channels or email lists. It is also vital to validate that these modifications do not inadvertently introduce side effects that impact the original template. You are looking for a state of isolation where the new detector functions independently while still benefiting from the structural integrity of the original design. By following a disciplined approach, cloning, targeting, filtering, and validating, you maintain a scalable observability foundation. This modular lifecycle for detectors essentially reduces the cognitive load on your team and ensures that monitoring grows in lockstep with your infrastructure. See you in the next lesson. Welcome back. In this session, we will examine the mechanics of building standalone detectors to gain granular control over your monitoring environment. When we rely solely on prepackaged alerts, we often find ourselves constrained by generic thresholds that do not align with our specific business logic or infrastructure nuances. Constructing a standalone detector allows you to pivot from passive observation to proactive engineering of your signal monitoring. The process begins in the dedicated alerting user interface, where you define your raw signal inputs. You are essentially crafting a query that filters the vast sea of metrics down to the specific subset that signifies a meaningful change in state. By selecting the correct metrics and applying initial dimensionality filters, you ensure that the detector operates only on relevant data. which is our first defense against irrelevant noise. Once you have identified the primary signal, the capability to build multi-condition threshold evaluation matrices becomes crucial for complex monitoring scenarios. A simple static threshold is rarely sufficient for production systems that exhibit natural variance, so we employ Boolean logic to correlate disparate data plots. For instance, you might want to trigger an alert only if CPU utilization exceeds a specific percentage while simultaneously detecting an increase in request latency. By using explicit Boolean operators, you can combine these distinct signals into a single detector, effectively creating a more precise representation of what constitutes an actual system failure versus a temporary fluctuation. This level of architectural rigor requires a deep understanding of how your metric streams interact under load. Defining precise trigger sensitivity is arguably the most sensitive aspect of detector configuration, as it dictates the signal-to-noise ratio of your operations center. Sensitivity is not merely about setting a number. It is about establishing a functional relationship between the state of your service and the urgency of the alert. We categorize these states using custom severity models ranging from informational notifications to critical emergencies. An informational alert might flag a minor cache churn that requires no immediate human intervention, whereas a critical emergency signal demands immediate attention for a platform outage. By mapping your specific detector outputs to these tiered severities, you provide the necessary context for teams to act effectively during an incident. Configuration of clear conditions is a frequently overlooked yet vital component for maintaining long-term monitoring health and preventing alert fatigue. If a detector triggers because a metric exceeded a threshold, the clear condition determines when that state is considered resolved. Setting the clear threshold lower than the trigger threshold creates a hysteresis effect, which prevents minor oscillations around the alert boundary from repeatedly opening and closing tickets. Without this deliberate separation between the triggering and clearing logic, your system will likely suffer from flapping, where an alert repeatedly transitions between active and resolved states. Managing this effectively ensures that the alert stays open as long as the underlying issue remains a genuine concern. Finally, the validation phase is where theoretical design meets the realities of your production data telemetry pipelines. Before pushing a new detector into the wild, you must observe its behavior against historical and live data to ensure your logic holds up under actual traffic patterns. This involves checking if the detector fires when you expect it to, and, perhaps more importantly, ensuring it remains silent when the system is healthy. You are essentially conducting a unit test for your alerting architecture using the current production stream as your test harness. Once you've confirmed that the end-to-end event generation aligns with your expectations, the detector is ready to serve as a reliable guardian of your system's performance. See you in the next session. Welcome to the chapter on muting rules orchestration, where we will examine how to programmatically suppress non-actionable alert noise during planned environmental changes. In any sophisticated observability architecture, the inability to silence alerts during maintenance windows leads directly to alert fatigue, a state where engineers essentially train themselves to ignore critical signals. Splunk Observability Cloud addresses this through muting rules, which provide a dedicated mechanism to prevent notifications from reaching responders. A common pitfall is the blanket application of these rules, which can inadvertently blind monitoring systems to genuine systemic failures occurring simultaneously with a release or an upgrade. To avoid this, we must adopt a mindset of surgical precision, defining boundaries that act as filters rather than global off switches for our alerting infrastructure. By leveraging dimension key-value pairs, we ensure that a muting rule meant for a database deployment in a specific zone does not silence an unrelated web server failure in another region. When we construct a muting rule, we are essentially defining a temporary override state for specific signal subsets. The orchestration of these rules involves establishing a robust scope, an active time window, and a clear intent for the lifecycle of that suppression. You should think of a scope as the union of specific dimensions that categorize your infrastructure, such as environment, service name, or availability zone. If you define a rule that targets all hosts regardless of their metadata, you risk creating a silent failure window that could mask a catastrophic outage. Therefore, the implementation of tight scoping parameters is not merely a best practice. It is a fundamental requirement for maintaining visibility integrity. We express these boundaries using the same dimensional filtering logic found throughout the platform, which ensures consistency when you move from visualizing data to managing alerts. Distinguishing between complete alert suppression and notification delivery suppression represents a crucial nuance in our operational workflow. In many scenarios, you may want the detector to continue evaluating the condition to ensure the logic remains healthy, but you wish to refrain from generating noisy notifications like PagerDuty alerts or Slack messages. Conversely, there are situations where you want to pause the detector in its entirety to conserve processing cycles or avoid logging historical state transitions during a known downtime. Mastering this distinction allows you to maintain clean audit logs that reflect the true state of your health checks versus the human-facing operational status. When we configure these rules, we also incorporate recurring schedules, which are particularly powerful for automated nightly maintenance tasks or weekly batch processing windows. Manual overrides provide a critical safety valve when an automated procedure encounters an unforeseen error or takes significantly longer than the initial maintenance window assumed. You should treat manual muting as an exception, a short-term tactical intervention while you investigate why the automated orchestration failed to close the window as expected. To maintain a healthy enterprise environment, auditability is paramount, and you should regularly review the list of active muting schedules. An orphan rule that was meant to expire but remains active can do significant damage to your observability strategy by creating a false sense of security. As you practice configuring these rules, prioritize defined dimensions that accurately reflect the blast radius of your infrastructure changes, ensuring that every suppression event is accounted for and temporary by design. See you in the next lecture. Welcome back. In this lesson, we will focus on the complexities of managing high-cardinality alert detectors within the Observability Cloud platform. High cardinality becomes a significant operational problem when the number of unique time series streams exceeds the capacity of an individual detective process or the platform limits. When you monitor environments with tens of thousands of container instances, each emitting unique metadata tags, the sheer volume of data can overwhelm a detector. You might notice that instead of receiving actionable intelligence, you are seeing plot cap constraints, where the system stops evaluating your logic because the scope has become too expansive. To resolve this, we must first look at the evaluation scope of our SignalFlow code. By moving filtering logic to the earliest point in the processing chain, we ensure that we only pay the performance cost for metrics that are truly relevant to the incident being tracked. If you find your detectors failing to trigger, it is often a sign that you have neglected to limit the dimensionality of the metric being processed before the aggregation step occurs. One of the most effective mechanical levers at our disposal is the application of spatial aggregations, which effectively collapses a massive population into a more manageable set of dimensions. Instead of attempting to monitor every individual ephemeral container, we should group these hosts into larger, logical buckets based on shared metadata, such as service name, cluster region, or environment phase. By performing this aggregation at the platform level, we reduce the cardinality of the input stream, which in turn reduces the likelihood of encountering execution performance degradation. Another powerful technique involves using top or bottom filtering statements within your SignalFlow definitions. By focusing only on the worst performing subsets of your fleet, you significantly reduce the amount of noise generated by healthy components that do not require manual intervention. This approach shifts the detector's focus away from individual ephemeral events and toward the macro-level state of your entire population, which is generally more indicative of system health. Structuring your threshold parameters to evaluate these aggregated macro states rather than individual units requires a shift in how we approach alert design. If you define a threshold based on an average value across a cluster, the noise floor remains stable even as the underlying container population expands linearly. This ensures that as your infrastructure grows, your alert sensitivity does not suffer from a corresponding increase in false positives. We must always weigh the utility of granular visibility against the risk of hitting platform limits that degrade system execution performance. When you notice that a detector is consistently hitting its maximum population limit, it is almost always a signal that your aggregation strategy needs to be applied higher up in the metric stack. By prioritizing performance through intelligent scope limitation and strategic filtering, You create a robust alerting architecture that scales alongside your infrastructure without compromising on diagnostic efficacy. I will catch you in the next lecture. Hello. In this lesson, we will focus on the tactical approaches required to minimize alert fatigue within the Splunk Observability Cloud environment. Alert fatigue represents a silent productivity killer in modern engineering organizations, often leading to team burnout and the eventual dismissal of critical system warnings. When we configure detectors, our technical objective is to ensure that every fired notification signifies an actionable event requiring immediate human intervention. The primary culprit for noise is frequently the use of arbitrary static thresholds that fail to account for the intrinsic volatility of cloud-native infrastructure. By transitioning from static limits to context-aware configurations, we significantly increase the signal-to-noise ratio of our monitoring posture. We must treat alert configuration as refined software engineering rather than simple threshold setting, necessitating a rigorous look at how our metrics behave over extended observation windows. Without these refinements, developers inevitably tune out the stream of notifications, creating a vulnerability where genuine systemic failures go unnoticed amidst a sea of false positives. A fundamental method for reducing noise involves the implementation of persistent duration windows within your detector definitions. Instead of triggering an incident the moment a single data point crosses a threshold, we can mandate that the signal must sustain that violation for a specified continuous duration. For example, if we expect transient CPU spikes during a background batch job, setting a 1-minute duration window effectively filters out these harmless peaks. This approach forces the monitoring system to ignore momentary jitter, ensuring that we only alert on sustained performance degradation or capacity exhaustion. You might be tempted to set these windows to be extremely short to capture immediate issues, but a balanced approach acknowledges that transient network congestion or internal rebalancing frequently resolves itself without operator interaction. Configuring a mandatory duration provides the buffer necessary to distinguish between temporary system instability and a hard failure state requiring remediation. Beyond duration windows, we must address the issue of flapping alerts, which occur when a metric fluctuates rapidly across a threshold boundary, causing the system to trigger and resolve repeatedly. To mitigate this, Splunk Observability Cloud allows for sophisticated logic and trigger sensitivities and custom clear conditions that force the metric to return deep into a healthy zone. Rather than resetting the alert the instant a metric falls just below the threshold, we can require the metric to maintain a safe level for a specific period or distance before the incident is closed. This provides a hysteresis effect that stabilizes the alerting cycle and prevents the persistent notification spam associated with threshold oscillation. By structuring these clear conditions carefully, we prevent the system from switching states prematurely, effectively dampening the chatter that often plagues highly dynamic environments during periods of moderate instability. It is also vital to account for data transport lag and processing latency when establishing our monitoring thresholds. Monitoring systems often ingest data from distributed collectors, and network partitions or serialization overhead can slightly delay the arrival of metric data points. If we set alert delays too aggressively, we risk reacting to incomplete data bundles or misidentified sequence gaps from the ingestion pipeline. By calculating the expected latency of our ingestion flow and applying an appropriate offset, we ensure that the detector evaluates a complete and accurate snapshot of our infrastructure state. Furthermore, avoiding static limits in favor of historical baselines allows our detectors to adapt to gradual changes in traffic patterns or seasonal load. Using statistical lookbacks rather than hard-coded values creates a more resilient system that understands what constitutes normal behavior for a specific time of day or week. Ultimately, effective alerting strategy requires an iterative loop of continuous tuning based on historical incident data. We must regularly review the alerts that have fired in the past week and evaluate whether those notifications led to meaningful action or merely contributed to the existing noise floor. If a detector consistently fires for minor issues that do not warrant a pager interruption, that detector should be modified to increase its threshold, extend its duration requirement, or trigger only a low-severity event. Operational monitoring noise is not an inevitable byproduct of complex systems. It is a structural flaw that we must consciously address through configuration discipline. As you refine your detectors, remember that the goal is trust in the system, because without that trust, Our complex observability dashboards lose their primary purpose. By systematically implementing these duration windows, intelligent clear conditions, and baseline-aware thresholds, you move toward a sustainable and efficient monitoring culture. See you in the next lecture. Welcome back. In this chapter, we will explore how to enhance dashboard usability by embedding contextual instructions and operational documentation directly into your visualization grids. When you are managing a complex distributed system, the cognitive load during an incident is already high. Adding explicit instructions to your dashboards transforms them from simple data displays into active runbooks that guide responders toward faster resolution. By utilizing markdown text blocks, you can ensure that the context behind specific metrics is immediately available to anyone viewing the charts. This practice minimizes the time spent searching for external documentation when every second counts during a production outage. You might wonder if adding text bloat is a concern, but when applied strategically, it provides the why behind the what that raw charts often fail to communicate. A well-placed header or a concise procedural note can prevent a junior engineer from misinterpreting a spike in latency as a system failure when it is actually a scheduled background process. To begin enhancing your dashboards, consider the layout text block as your primary tool for structuring information. These blocks allow for rich text formatting, which means you can use headers to designate clear sections of your dashboard, such as separating high-level health signals from granular infrastructure metrics. Organizing visual sections with bold headers makes it easier for the human eye to scan the screen and find the relevant data segment quickly. Markdown support is quite robust in this environment, giving you the ability to create lists or emphasize critical warnings. Remember that these instructions are most effective when they map directly to the service architecture depicted in the charts themselves. If a chart tracks memory saturation, placing a small markdown block nearby with a link to the relevant service map gives the user a clear path for further investigation. Embedding context-specific hyperlinks is perhaps the most significant functional improvement you can make to your observability workspace. By directing teams to internal escalation workflows or specific runbooks stored in your documentation portal, you create a seamless bridge between the monitoring platform and the operational manual. This prevents the common scenario where an engineer sees an issue but has to navigate through disjointed tabs or wikis to figure out the standard operating procedure for mitigation. These links should be kept concise and labeled clearly to reflect the action they support, such as triggering a redeploy or scaling a compute group. When formatting your Markdown, ensure that these links open in a new tab to avoid losing the current view, allowing for a side-by-side comparison of the chart and the diagnostic guide. Integrating these resources creates a self-documenting environment that preserves organizational knowledge where it is actually used. Inline descriptions serve as another layer of clarity for complex analytical charts that might otherwise be ambiguous. Often, charts aggregated with specific transformations or time shift functions appear straightforward to the author, but can be confusing to a secondary responder who did not build them. Providing a brief note explaining the logic behind a curve, such as noting that a specific plot represents a rolling average over the last 4 hours, clarifies intent and reduces uncertainty. During an active incident investigation, this transparency is invaluable for maintaining trust in the telemetry. You should aim to document the boundaries of what is considered normal behavior for a metric within these descriptions. If a chart typically displays a high level of periodic noise, stating this clearly prevents unnecessary escalations caused by perceived anomalies that are actually expected system characteristics. Layout and placement are critical to ensuring that these instructions contribute to, rather than distract from, the visualization of the data. You should treat the dashboard as a narrative flow, where instructions guide the user's gaze from individual components toward a logical conclusion. Start by placing high-level instructions at the top to set the scene, and add specific, chart-local notes next to the most complex or critical visualizations. Avoiding excessive text is equally important. Prioritize brevity and ensure that each block of instructions provides actionable information. By adhering to these standards, you turn static observability into a dynamic tool that directly integrates with your team's incident response lifecycle. This approach fundamentally improves the consistency of triaging efforts across your entire engineering organization. See you in the next session. Welcome to our exploration of single-instance dashboards. In this session, we will examine how to architect highly reusable interfaces using dynamic variables to eliminate redundant configuration. Building multiple dashboards for identical environments is a common pitfall that leads to technical debt and maintenance nightmares. Instead of cloning a dashboard for every production, staging, or development environment, we leverage dashboard-level variables to act as global filters. When we define a variable, such as environment or cluster name, we are essentially creating a shared token that permeates every chart within that dashboard. This token must be mapped directly to the underlying signal filters of your charts. By standardizing these mappings, we ensure that a single change to a drop-down menu propagates across every visualization simultaneously. The primary goal here is to maintain a single source of truth while providing the flexibility required to inspect disparate infrastructure segments on demand. The architecture of a well-designed dashboard relies heavily on how we manage variable inheritance. When a user selects a value from a filter dropdown, the Splunk Observability Cloud engine updates the global context for the dashboard session. Every chart utilizing that specific token evaluates its signal flow by injecting the selected variable into its metric query. To ensure this happens cleanly, you must enforce strict parameter definitions at the dashboard level rather than hard-coding values within individual metric finder queries. Think of this as a dependency inversion principle, where the chart does not know about the environment. It only knows about the token it receives. This abstraction layer is what allows your layouts to remain consistent and stable during user interactions. Layout stability is another crucial factor when orchestrating dynamic dashboards. A common issue developers face is screen stuttering or unwanted redraws when switching between inputs. This usually occurs when the dashboard tries to re-render component containers that do not have explicitly defined dimensions or stable metadata indexing. When you optimize your dashboards, you should always favor static grid layouts that accommodate the maximum expected content. By ensuring that your metadata indexing patterns remain predictable, the Observability Cloud can perform lookups for the new signal slice without needing to restructure the document object model of the visualization surface. This leads to instantaneous data updates that feel fluid rather than jarring to the operator. Effective metadata usage acts as the backbone of performant single-instance dashboards. Since the system must query high-cardinality data, your filters should be grounded in indexed fields that narrow down the result set as early as possible in the execution pipeline. When a user switches an environment variable, the underlying SignalFlow program needs to perform a minimal set of operations to resolve the new subset of data. If your chart queries are bloated with complex logic that cannot utilize index-based filtering, you will encounter latency spikes despite having a well-structured dashboard. Always verify that the variables you expose are backed by indexed metadata fields to keep the transition speed high and the overhead low. Designing for reusability also means being thoughtful about the visual grouping of charts. Since all charts on the dashboard will respond to the same variables, you should organize your workspace in a hierarchical manner that mirrors the logical structure of your services. For example, if you provide a cluster-level variable, every row in your layout should provide supporting metrics that explain the health of that cluster from different perspectives. This creates a cohesive narrative for the end user. If the dashboard is too wide or contains too many disparate signals, the cognitive load increases, and the benefit of having a unified dashboard is lost. Maintain focus by restricting each single instance dashboard to a specific architectural layer of your stack. Finally, consider the user experience of your peers who will interact with these dashboards. A dashboard should be self-documenting, meaning the intended use of the top-level filters should be obvious immediately. If you have complex variables, ensure the display labels are descriptive and that the default selections reflect the most commonly monitored state. Avoid nested variables unless absolutely necessary, as they increase the complexity of the internal signaling state and can be harder to troubleshoot when data fails to appear as expected. By keeping the variable relationships flat and predictable, you empower your team to resolve incidents faster without having to navigate through a labyrinth of customized, fragmented, and hard-to-maintain dashboard instances. I will see you in the next lecture. Welcome back. Let's explore how to integrate contextual metadata directly into your time series charts to improve diagnostic clarity. In this session, we investigate the mechanics of event visualization techniques, specifically focusing on how to overlay operational context onto metric streams. By superimposing events such as deployment markers, configuration changes, or detector alerts, you create a synchronized timeline that transforms raw data into a narrative. We will examine how a standard metric line, such as memory utilization, gains immediate diagnostic value when it is visually aligned with a deployment event. This alignment is not merely an aesthetic choice, but a fundamental requirement for rapid root cause analysis in distributed systems. When you can see the precise timestamp of a code push against a sudden spike in latency or resource consumption, the connection between cause and effect becomes undeniable. We will discuss the underlying architecture of these overlays, ensuring you understand how Splunk Observability Cloud bridges the gap between discrete event logs and continuous metric streams. Configuring these overlays requires an understanding of how event feeds are ingested and subsequently mapped to your graphical workspace. You start by selecting an appropriate event feed source, which can range from deployment automation tools to infrastructure management platforms that emit events via predefined API calls. It is essential to filter these feeds based on source types or severity tags to prevent your charts from becoming cluttered with irrelevant noise. If you enable every possible event notification, you will find that the chart loses its ability to highlight the occurrences that truly matter during an incident. Therefore, you must be disciplined in your selection criteria, perhaps choosing to visualize only critical deployments or high-severity alert triggers. Once the source is selected, the system will pull these events into the time series space, rendering them as vertical markers or distinctive icons along the horizontal axis of the chart. Beyond simple overlay placement, the visual presentation of these events is a critical component of effective dashboard design. You must adjust the display properties to ensure that your events are easily distinguishable from the actual metric lines representing your system throughput or health. I recommend using high contrast colors and distinct line styles to differentiate a deployment marker from a transient data point. Furthermore, integrating event list panels allows you to interact with the narrative. Hovering over a marker in the chart should dynamically highlight the corresponding detail in the event log table beneath or beside the visual. This interaction model enables you to instantly pivot from identifying a correlation in the graph to reading the metadata of the event itself. By investing time in configuring these display properties, you minimize the cognitive load required by your on-call engineers when they are investigating production issues in a high-pressure environment. Ultimately, the goal of utilizing these event visualization techniques is to reduce the time from detection to remediation. Consider a scenario where a service starts exhibiting high error rates. Without event overlays, you might spend an uncomfortable amount of time manually checking CI/CD logs or configuration management history to identify recent changes. With an event feed superimposed on your error rate chart, you can immediately spot if the rise in errors corresponds precisely to a deployment marker, indicating that the new version likely introduced a regression. This temporal alignment allows you to treat the infrastructure and the application as a single, cohesive system, rather than viewing metrics and events as disjointed pieces of information. As we refine our approach to dashboarding, remember that context is always the most valuable commodity in observability. I will see you in the next lecture. Welcome back. In this session, we investigate the mechanics of local data links, which serve as the connective tissue between disparate diagnostic views within your observability environment. When we construct custom dashboards, our primary objective is to facilitate a rapid transition from high-level observation to granular investigation. Local data links allow us to achieve this by embedding interactive anchors directly within chart cells. Instead of forcing a user to manually navigate through menu structures or search bars, these links transform static visualization elements into dynamic portals. By mapping contextual dimension keys, we ensure that movement between views preserves the underlying state and filtering criteria. This creates a predictable navigational path that scales across teams and services, effectively reducing the cognitive overhead required to resolve incidents. To implement this, you must understand how to map dimension keys into dynamic outbound URL destination strings. When creating a link, you define a template that acts as a blueprint for the interaction. Within this template, you use variable placeholders that correspond to the dimensions present in your metric data. For instance, if you are monitoring a specific service, You might pass the service name dimension directly into the URL query parameters of a secondary dashboard or an external ticketing system like Jira or PagerDuty. The system performs a runtime substitution, replacing the placeholder with the actual value associated with the specific data point you have clicked. Preserving temporal context is equally critical during these navigations. When a user clicks a cell, they expect the target environment to reflect the same time frame they were just analyzing. By appending time window properties to our target URL strings, we ensure that the investigation continues exactly where it left off. You configure this by utilizing built-in URL parameters that signify the start and end of the current chart duration. If a developer notices an anomaly and a spike between 2 and 3 o'clock, the link transition must carry those timestamps over to the target dashboard. Without this, the investigator would be forced to manually reset time filters, adding unnecessary steps and potentially losing sight of the specific transient event. Advanced implementations involve conditional linking logic that dynamically alters the link destination based on the selected data point. You might have a single chart displaying multiple services, where each service demands a different investigation workflow. Through the configuration interface, you can specify that clicking on a critical service routes the user to a deep dive APM trace view, while clicking on a supporting infrastructure service routes them to a system-level resource dashboard. This logic prevents clutter and ensures that users are always presented with the most relevant information for their specific context. This adaptability is what elevates a chart from a simple reporting tool to an operational decision-making engine. Validating these links is a step that cannot be overlooked if you want to maintain a reliable diagnostic pipeline. It is not uncommon for dashboards to be updated or for metric dimensions to be renamed, which can easily break hard-coded navigation paths. Whenever you define a link, perform a test by clicking the generated element to ensure the target environment opens with the expected parameters correctly populated. Look for empty results or error pages in the target dashboard as primary indicators of broken mappings between dimension keys and query parameters. By performing these brief, systematic checks during the creation process, you ensure that your team experiences a seamless journey from high-level summaries down to the root cause. See you in the next lecture. Hello, and today we are focusing on the mechanics of customizing alert notifications to ensure that your on-call engineers receive actionable intelligence the moment an incident occurs. In this lesson, we will explore how to transform generic alerts into comprehensive diagnostic packets that minimize the time spent context switching between platforms. A well-crafted alert notification should serve as a primary diagnostic tool rather than a simple trigger for investigation. When we configure notification templates in Splunk Observability Cloud, we have the ability to inject dynamic metadata variables that provide immediate visibility into the state of the system at the time of the violation. By utilizing token substitution syntax, you can embed specific metric values, such as the exact CPU percentage or memory utilization, directly into the subject lines and bodies of your alerts. This approach allows an engineer to understand the magnitude of an issue before they even open a dashboard or investigate the underlying service. For example, instead of receiving a generic notification that a host is experiencing high latency, a customized alert can deliver a message stating that host 123 is currently reporting a P99 latency of 450 milliseconds across the production environment. Effective alert messaging relies on the strategic inclusion of dimensionality and runtime context. When defining these notifications, you should incorporate tags such as the specific container ID, the service name, or the geographical region where the failure is manifesting. These dimensions assist in routing and prioritizing issues, especially when coupled with severity flags that determine whether a dispatch should be treated as a critical page or a low-priority notification. We also encourage embedding direct links to relevant runbooks or documentation within the message payload to ensure that responders have step-by-step resolution procedures immediately available. By structuring the message layout to present the most critical information at the top, you create a more efficient incident response workflow that prevents the common pitfalls of alert fatigue and information overload. The technical implementation of these messages requires a disciplined approach to template authoring to ensure that the injected variables remain consistent across different communication channels like Slack, PagerDuty, or standard email. When you are writing your templates, You must verify that the token syntax correctly maps to the object properties available within the metrics pipeline. If you attempt to call a dimension that is not attached to the specific metric time series, the resulting notification will produce an empty or null value, which degrades the perceived reliability of your alerting system. Therefore, it is standard practice to test your alert templates under varied conditions to ensure that the placeholders resolve correctly during both transient spikes and sustained violation periods. Consistently including the duration of the violation also provides the responder with a sense of whether the system is currently recovering or entering a more severe state of failure. Ultimately, the goal is to bridge the gap between simple binary state changes and complex systemic observability. An effective alert should explain the what and the where with sufficient precision that the initial dashboard lookup becomes a verification step rather than a discovery mission. By standardizing the way your team formats these messages, you create a common language across your infrastructure, making it significantly easier to maintain and troubleshoot your detectors over time. As you refine your notification strategy, focus on the metadata that is most frequently queried by your team during an active incident. This data-driven approach to alerting is what separates robust monitoring setups from those that generate noise without providing value. I look forward to discussing how these practices integrate into your existing workflows in the next segment. Welcome back. In this session, we will examine the mechanisms behind visualization errors and how to restore data integrity in your dashboards. When a chart fails to render or displays incomplete data, the root cause is often rooted in operational delays or configuration mismatches. Data points arriving after the platform's standard processing window will not be reflected in your visualizations, creating the illusion of gaps in your metrics. To address this, it is essential to first verify that your underlying data models are actively receiving packets from the source environments. You should inspect your network ingestion logs and the connectivity status of your data collectors to ensure no packet loss is occurring at the source. If the ingestion pipeline is healthy, the issue often resides in the representation layer itself rather than the data source. Discerning whether a problem is a systemic ingestion delay or a local rendering error is the first step in effective troubleshooting. Another frequent culprit for distorted visual representations is the mishandling of null values in sporadic metric streams. If you have a sensor that only reports intermittently, the default behavior might be to leave a gap in the timeline, which can be disorienting during postmortem analysis. You can configure explicit extrapolation policies such as null, zero, or last value propagation to ensure your charts maintain continuity. When you select the last value policy, the system carries the previous metric state forward until a new data packet arrives, effectively smoothing out transient dropouts. Conversely, choosing a null policy makes it clear that no data was received during that time frame, which is often preferable for debugging hardware heartbeat issues. Balancing these policies requires a clear understanding of whether your data represents a continuous flow or event-based snapshots. Analytical aggregations frequently break due to hidden dimension name collisions occurring within your metric metadata. When multiple sources emit data with identical dimension keys but incompatible value types, the aggregation engine cannot reconcile the resulting streams. This scenario manifests as abrupt flatlines or unexpected calculation errors because the engine effectively ignores the conflicting data slices to maintain process stability. To resolve this, you must audit the incoming metadata tags for consistency and ensure that dimension naming follows a strict, centralized convention. If you find that one set of source agents is sending inconsistent labels, adjusting the processing logic at the ingestion layer is the only way to re-enable functional aggregations. Proper governance of dimension namespaces prevents these invisible errors that typically evade simple chart-level checks. Finally, we must address the issue of graph truncation caused by excessive plot cardinality within a single dashboard component. When a query targets a high-cardinality metric that has thousands of unique dimension values, the visualization layer will often truncate the output to protect system memory and browser performance. This usually results in a chart that appears incomplete or suggests an incorrect sum because only a subset of the actual data series is being plotted. To manage this, you should look for opportunities to apply grouping functions or filters that reduce the total number of series visualized in one instance. By narrowing down the specific subset of signals, you not only improve the clarity of the visualization, but also ensure that the analytical engine can process the requested data efficiently. Understanding the limitations of your visualization assets regarding cardinality is crucial for maintaining usable, high-performance monitoring environments. We shall continue our work in the next segment. Welcome back. In this session, we will examine the mechanics of aggregating global values from distributed infrastructure fleets to achieve macro-level visibility. Working with large-scale environments requires us to move beyond individual host monitoring and instead focus on the aggregate health of our systems. When you manage hundreds of distributed database instances, looking at each one individually is not only impractical, but also masks the broader patterns that define your application's performance. By applying spatial aggregation functions directly within the streaming data layer, we can collapse vast datasets into meaningful signals. We frequently rely on the sum transformation to track total transactional throughput, providing a clear view of aggregate load across global regions. If you are tracking database queries, summing these values allows you to verify that your global egress is within defined capacity limits. This approach requires that your metric streams be normalized effectively before the transformation is applied. Once you move into this tier of observability, the objective shifts from local debugging to system-wide capacity planning and trend identification. To isolate specific behaviors, we often need to look past simple sums and leverage maximum or average aggregate functions. For instance, calculating the aggregate maximum across a cluster is a standard technique for identifying worst-case performance scenarios. If one node in a fleet of 50 enters a degraded state, an aggregated maximum will surface that spike, whereas a simple average might smooth it out until it becomes invisible. We achieve this by using group-by modifiers, which allow us to slice our metrics by specific dimensions like cloud region or availability zone. This granularity ensures that while we are viewing global statistics, we still retain the capability to pin down the root cause to a specific geographical footprint. You should approach your query design by thinking about which levels of the stack need to be aggregated and which need to remain as discrete dimensions. The balance between granular data points and wide aggregators is the key to managing high cardinality environments effectively. Mathematical accuracy in global statistics is often threatened by missing stream conditions, which represents a subtle but critical challenge in telemetry. If a subset of your distributed instances stops reporting data, a simple sum could suddenly drop, leading you to believe that your actual transactional volume has decreased when in reality, your observability pipeline is experiencing partial loss. To handle this, we must ensure that our calculations account for stream availability by defining how missing values should be treated. In many cases, it is safer to treat missing streams as null rather than zero, as zero implies that no activity occurred rather than an absence of instrumentation. This distinction matters because it impacts alerting thresholds and capacity prediction models that rely on historical averages. By refining your aggregation expressions to be aware of the state of the underlying streams, you can build dashboards that do not just show what is happening, but also reflect the reliability of the telemetry itself. We'll see you in the next lecture. Welcome back. In this chapter, we will explore the nuances of combining distinct data streams to derive meaningful insights that go beyond elementary metric visualization. When we interact with the chart builder, we often find ourselves needing more than just a single raw metric to tell a complete story. We often need to create higher order metrics by combining several independent signal lines into a unified mathematical formula. Splunk Observability Cloud facilitates this by assigning alphabetical plot handles, typically starting with the letter A for the first series, to every metric signal we define. Once these handles are established, we can reference them directly within a custom formula expression to perform arithmetic operations. For instance, if you have a metric for successful cache requests assigned to plot A and a metric for total cache requests assigned to plot B, you can define a new composite plot using the expression AB to calculate your actual cache hit ratio. This ability to synthesize data at query time significantly reduces the need for heavy pre-processing or complex ETL pipelines before data even reaches your monitoring environment. A crucial aspect of managing these composite metrics is the ability to handle dependency plots without cluttering your visualization. Frequently, you might require a base metric to calculate a derivative, yet you have no desire to actually see the base metric represented on the final graph. You can achieve this by marking specific plot handles as hidden, which allows them to remain active in the background as providers for your formula while keeping your interface clean and focused. This technique is particularly powerful when you are layering raw throughput metrics against a calculated statistical trend line, such as a moving average or a standard deviation baseline. By keeping the underlying components invisible, you ensure that the end user can clearly perceive the trend line or the final ratio without being distracted by the intermediate signals that were required to construct it. Mathematical complexity inevitably requires a robust approach to execution precedence and logic. When you construct multi-stage analytical formulas, the system processes your equation based on standard algebraic rules, but you must be intentional about how you group these operations. Using parentheses within your expression field is not merely good practice. It is essential to ensure that your addition, subtraction, multiplication, and division operations occur in the intended sequence. Think of these expression fields as small code blocks where the order of operations governs the final result. If you are chaining multiple analytical steps, consider how each variable depends on the preceding handle. If you modify the source data for plot A, all downstream composite expressions referencing A will automatically update, which provides a consistent and reactive analysis layer across your charts. Managing these formulas also involves an awareness of how different granularity and rollup functions interact within the same chart. When you combine plots that originate from different sources or have varying resolution strategies, the system must harmonize these signals to perform the math accurately. You should ensure that your analytic transformations, such as aggregations or time window functions, are applied consistently across contributors if you intend to produce a unified result. If one contributing signal is averaged over a 5-minute window and another is queried at peak resolution, the resulting division or subtraction may reflect a mathematical discrepancy rather than a true operational reality. Always verify the underlying data resolution and rollup settings for every handle involved in your equation to maintain total accuracy in your derived metrics. As you build these advanced views, keep in mind that the primary goal remains clarity for the end recipient of the dashboard. While technical depth is impressive, the value of a composite formula is realized only when the resulting plot answers a specific operational question. Use labels to clearly define your formulas in the legend and refine your y-axis formatting to accommodate the ranges that your calculations might produce. A calculated percentage, for example, looks far more professional and readable when expressed with fixed point decimals than when presented in raw machine form. By mastering the interaction between these hidden dependency plots and the final visible output, you transform the chart builder from a simple viewer into a powerful mathematical engine that surfaces hidden dependencies and non-obvious performance characteristics. See you in the next session. Welcome to the chapter on time shift comparisons. We will explore how to overlay historical data onto live metrics to identify trends and detect anomalies. In observational analysis, the ability to place current performance in a historical context remains one of the most powerful tools in our diagnostic arsenal. By leveraging time-shifted data signals, we move beyond simple real-time monitoring and begin to understand the rhythm of our infrastructure. When we look at a single line on a chart, we lack the necessary baseline to differentiate between a scheduled batch job and a genuine incident. A time shift transformation effectively creates a ghost of the past, projecting a previous window onto our current dashboard canvas. This alignment allows us to verify if an observed latency bump is actually a recurring pattern we have seen before, such as a predictable Monday morning spike. Precise comparisons across fixed temporal cycles, such as week over week or hour over hour, enable us to evaluate the impact of code deployments against stable historical baselines. These transformations are not merely aesthetic, they are functional, allowing us to perform arithmetic operations against the shifted data. By applying these specific analytical functions, we gain the ability to calculate variance between what happened yesterday and what is happening right now. The mechanics of this implementation involve applying a time shift analytical transformation directly to a specific data stream within the metrics pipeline. When we configure these signals, we essentially tell the observability platform to pull the data from a defined offset, such as 7 days prior, and align it with the incoming stream. Once both the real-time line and the historical baseline occupy the same temporal space, we can visualize the delta using percentage variance functions. This specific calculation is vital when you need to distinguish between minor deviations that fall within a normal operational profile and legitimate novel degradation anomalies. For instance, if your service traffic consistently climbs during specific user activity windows, the time-shifted plot will mirror this movement, preventing the creation of false positive alerts. It is crucial to recognize that this is an analytical layer, meaning we are not changing the underlying data resolution or storage, but rather changing how the data is rendered at query time. Maintaining this distinction is important because it keeps your core metric data intact while providing the necessary flexibility to perform comparative diagnostics on the fly. When we rely on visual inspection alone, we risk falling into the trap of cognitive bias, where our eyes see patterns that do not exist or overlook subtle shifts in performance behavior. By establishing a formal, programmatically defined comparison, we remove the guesswork and provide our team with a common frame of reference. If you decide to overlay a previous week's performance over current production metrics, you create a tangible benchmark that holds historical context. This becomes exceptionally useful during post-incident reviews where you must determine if the current system state represents a return to normalcy or a continued deviation from the expected performance profile. Utilizing absolute variance lines allows us to identify the specific magnitude of a slowdown, transforming a vague feeling of performance degradation into a precise metric value. We then use this data to inform our alerting logic, ensuring that we only trigger notifications when the variance exceeds a statistically significant threshold. This approach keeps engineers focused on genuine problems while minimizing the noise that often accompanies naive alerting strategies. See you in the next lecture. Welcome back. In this session, we will explore the application of ratios and percentages to transform raw metrics into actionable insight. Working with raw volumetric data often leads to dashboards that are difficult to interpret when the underlying infrastructure scales. If you simply chart the total number of errors, a spike in traffic might look like a system failure even if your error rate remains constant. To solve this, we shift our focus toward normalized ratios, which provide context by relating one metric to another. By dividing the count of error events by the total transaction volume, we derive a percentage that accurately represents the health of a service regardless of its current load. This approach is fundamental to managing error budgets, as it allows you to define service-level objectives that remain stable even when your application experiences massive fluctuations in user traffic. When monitoring system resources, evaluating raw values in isolation rarely tells the whole story. For instance, knowing that a server has 2 gigabytes of memory currently in use is numerically correct, but it lacks the necessary context of the system's total capacity. To make this data meaningful, we must calculate the utilization percentage by dividing the captured usage value by the absolute hardware constraint. By then applying a scale function, we ensure that our output consistently falls within the intuitive 0 to 100 range, which is critical for standardized dashboard design. This consistency allows operators to glance at a panel and immediately perceive the level of resource pressure without performing mental arithmetic on fluctuating capacity figures. Normalization is also a powerful technique for analyzing growth trends across disparate data points that exist in different units of measure. When you standardize these values into percentages, you create highly portable metrics that do not depend on the specific scale of the workload. This is especially useful when constructing dashboards intended for diverse environments, such as staging clusters versus production clusters. A panel configured to show a percentage-based growth trend will function identically in both environments, even if the raw volume of events in production is magnitudes higher than in the staging environment. This abstraction layer effectively decouples your operational visibility from the volatile nature of the underlying hardware or software components. Building these ratios requires a clear understanding of the mathematical transformations available within the platform. You are essentially creating a new, derived signal from existing time series data, which allows you to track efficiency through a more refined lens. When configuring these transformations, consider how the aggregation intervals affect your results, particularly when dealing with noisy metrics. If you observe volatility in your percentages, you may need to adjust your rollup functions to smooth out short-term fluctuations before the ratio calculation occurs. Properly crafted ratios will help you distinguish between transient spikes and meaningful signs of system degradation, ensuring that your alerting thresholds are grounded in reality. We'll catch you in the next one. Welcome back. In this lesson, we explore how time window functions allow us to manipulate metric data streams, focusing on the fundamental distinction between moving and calendar-aligned intervals. When we approach the analysis of metric data, we often deal with volatile signals that contain significant noise, making it difficult to discern long-term trends or verify compliance against predefined objectives. Time window functions provide a necessary mechanism to smooth this volatility by aggregating data points over defined durations, rather than treating every individual data point as an absolute truth. A moving window function calculates results based on a trailing interval that shifts continuously with time, effectively capturing trends relative to the current moment. In contrast, a calendar-aligned window binds its calculations to fixed temporal anchors, such as the start of a day, a week, or a month. Understanding the structural difference is the first step in applying the right analytical tool to your monitoring requirements. You must decide whether your objective requires a continuous assessment of recent behavior or an audit of performance against rigid temporal boundaries. To filter out short-term spikes in network throughput, we frequently employ rolling average functions, which act as a smoothing filter over a constantly shifting window of past data. By configuring a rolling average, you take a specified number of data points or a duration of time and compute a mean that ignores transitory anomalies. This ensures that your visualization reflects the underlying system capacity rather than alerting on every minor, non-impactful ingestion burst that occurs during routine operation. However, the choice of window length is a critical balance between responsiveness and clarity. If you set a window that is too short, the visualization remains sensitive to noise, defeating the purpose of the transformation. Conversely, setting a window that is too long obscures significant, genuine performance degradation by diluting the signal too heavily, making it harder for you to act decisively when a genuine bottleneck arises. While moving windows excel at trend analysis, calendar-aligned windows are indispensable when dealing with strict service-level agreements that demand compliance reporting. If a contract requires that a system remains under a certain threshold for a specified percentage of each calendar month, you cannot use a simple trailing interval because the result would vary depending on the exact second you query the metric. Instead, you apply calendar window maximums or averages that reset at the beginning of each defined period, such as midnight on the first day of the month. This provides an absolute, auditable record of performance that aligns with external reporting cycles. By utilizing these distinct windowing strategies, you gain the ability to both optimize your system in real time through noise reduction and maintain governance over long-term performance expectations. Mastering these mechanics ensures that your metrics accurately represent the context of the operational environment you are monitoring. See you in the next lecture. Welcome to the chapter on signal subset filtering, where we learn to isolate specific metrics within complex streams for granular analysis. We will explore how to target subsets of data to perform precise mathematical transformations without impacting your entire infrastructure population. When we approach observability, we often deal with an overwhelming volume of metrics flowing from diverse services and hosts. It is rarely useful to apply the same analytical function, such as a rate or a moving average, to every single data point originating from an entire cluster. Instead, think of your metric stream as a collection of individual signals that may require different treatments depending on their specific characteristics. Applying targeted analytical functions exclusively to precise subsets involves defining filter statements within your SignalFlow blocks that act as surgical tools. By narrowing our focus, we ensure that our computations, such as aggregations or statistical transformations, produce meaningful insights rather than noise. This approach allows us to isolate specific groups, like a set of canary nodes or a failing microservice, and apply specialized logic only where it is strictly necessary. Keeping other parallel streams untouched ensures the integrity of the broad view while we perform deep dives into problematic areas. Constructing granular, localized filter statements requires a firm grasp of how metadata dimensions interact with our processing logic within the Splunk Observability Cloud environment. When we utilize SignalFlow, we aren't just selecting data, we are orchestrating a pipeline of operations that respect the dimensional nature of our time series. For instance, if you have a wide stream of CPU metrics arriving from every host in your fleet, you might find that the global average hides the behavior of a specific subset of hosts running a high-load batch job. By applying a filter specifically for the host.group or service.name dimension, we can isolate just that subset to apply a distinct mathematical function. This function might calculate the delta or a specific percentile distribution exclusive to that group, leaving the remaining cluster data available for comparison or standard monitoring. It is a refinement process, effectively moving from high-level observation to low-level forensic scrutiny within a single coherent analytical block. A common requirement in large-scale architecture is identifying the extremes of your system's behavior, often characterized by the highest resource consumers. We use top and bottom selection filters to systematically isolate these entities, which allows us to focus our processing rules on the outliers that truly matter. Imagine a scenario where you want to apply a smoothing function or a trend analysis only to the top 10% of services experiencing memory pressure. Using a filter that ranks signals based on their recent value distribution is a quintessential example of efficient subsetting. By wrapping our signal in a function like top or bottom, we discard the noise of stable, healthy entities and dedicate our compute resources to the signals that demonstrate anomalous resource consumption. This is not merely about visualization, but about ensuring that our subsequent detectors and alerts are triggered only by legitimate deviations within the most critical segments of our infrastructure population. When dealing with sprawling, complex microservices architectures, a single filter is often insufficient to achieve the necessary level of specificity for root cause analysis. This is where nesting multi-dimensional filtering criteria becomes indispensable. You might start by filtering for a specific region, then further subset by a specific Kubernetes namespace, and finally refine the selection by a unique deployment version or canary tag. These nested filters behave much like a tiered sieve, allowing us to perform highly localized evaluations of service health before we even trigger an alert or a dashboard visualization. By stacking these filters, we ensure that our analytical logic remains deterministic and targeted, even when the underlying data is vast and deeply dimensional. It prevents the common pitfall of overaggregation, where valuable information is smoothed out or bundled into a useless global metric that hides the real issues occurring in small, isolated corners of the environment. Implementing these focused analytics requires an understanding of how signal streams flow through the processing engine. Because every transformation in Splunk Observability Cloud consumes resources, being deliberate about which signals are processed is not just a best practice, but a requirement for maintaining an efficient monitoring framework. When you define a filter within your SignalFlow code, that filter acts as a gateway. Everything that does not match is excluded from the subsequent mathematical operation, which inherently reduces the processing overhead. This allows your dashboard charts and detector logic to execute faster and more reliably. It is a philosophy of simplicity. Apply functions only where needed, on the data that truly matters, and always maintain clear mental boundary lines between your global monitoring signals and your detailed, subset-specific investigation streams. See you in the next lecture. Welcome back. In this chapter, we will master the systematic diagnosis of detector failures and logical inaccuracies to ensure your alerting environment remains reliable and precise. To diagnose operational failures in Splunk Observability Cloud, one must first establish a baseline for how detectors interpret incoming data streams. Detectors are constructed upon SignalFlow, the underlying analytical engine that processes continuous metric data against set thresholds. When an alert fails to fire during a known infrastructure outage, the primary suspect is often the logic path rather than the platform itself. You must examine the SignalFlow program to verify that the query is correctly capturing the intended metric time series. If a detector is not triggering, it may be due to missing input dimensions that are required by your conditional filtering statements. By validating that your dimensions are correctly tagged at the ingestion level, you ensure that the detector can effectively segment the data it needs to monitor. Data delays present a common challenge that can lead to evaluation gaps, creating a false sense of security where an alert should have triggered but did not. When metrics are ingested with latency, the detector might miss the specific window of time where a threshold was crossed because the data points arrived after the evaluation interval had already passed. Parsing internal detector evaluation logs allows you to trace the specific processing flow and identify if your data resolution settings match the reporting frequency of your agents. It is important to distinguish between genuine platform processing delays and inherent network latency caused by your observability pipeline construction. By auditing these logs, you can determine if the detector is receiving incomplete datasets, which often manifest as intermittent missing values during periods of high system load or network congestion. Faulty threshold configuration often sits at the root of what users perceive as platform errors, but these are typically issues in how the detector parameters were initially defined. When a detector is too sensitive, it generates noise, while overly broad thresholds result in silent failures. You should rigorously test your detectors against historical time ranges to see how they would have behaved during past incidents. If your detector uses static thresholds, consider whether the underlying metrics exhibit seasonal fluctuations that a static value cannot adequately represent. Introducing dynamic thresholds or relative changes, such as percent changes over time, often solves the problem of needing to constantly recalibrate static limits. Always map your detector logic back to the business outcome you are trying to measure, ensuring that the dimensions utilized are granular enough to support the specific alerts you require. Analytical errors within active detectors frequently arise from complex aggregation functions that lose detail when applied over too large a population. If you are aggregating across many hosts, the signal can become diluted, causing an alert to fail on a single faulty node within a healthy collective. To counter this, consider using grouping functions that maintain dimension integrity, allowing the detector to alert on individual instances when they deviate from the norm. Furthermore, verify that your conditional filtering statements are not mutually exclusive or erroneously nested, as this is a common point of failure for sophisticated detection logic. Reviewing the metric types, specifically whether you are using gauges or counters, will inform how your SignalFlow logic should handle null values during unexpected system restarts. Ensuring that your logic handles gaps in data explicitly by using fill functions will prevent your alerts from entering an unknown state during transient infrastructure blips. See you in the next lecture. Welcome to this module on troubleshooting alert states where we will explore how to resolve persistent detector issues and improve your monitoring reliability. We are going to examine the mechanics behind stuck alerts and how to effectively remediate them. When a detector remains in a triggered state despite metrics returning to acceptable levels, the root cause is often a latent data gap or a misaligned clear condition. If the detector evaluates incoming data points but fails to receive a signal to clear, it remains locked in an active state. You should first inspect the detector logic to ensure that the clear condition is explicitly defined and not implicitly reliant on the disappearance of a signal. Sometimes the system assumes that the absence of data means the alert should clear, but if there is no data coming in at all, the detector might simply hold the last known status. To resolve this, you can define an explicit extrapolation policy within your alert definition, which forces the system to treat gaps in data as a specific value, such as 0 or the last observed value, rather than simply ignoring the gap. This prevents the state machine from hanging indefinitely while waiting for a signal that may not arrive during periods of low activity. False positive trigger loops are another common challenge, particularly in environments with unpredictable workload bursts. These loops occur when trigger sensitivities are set too aggressively, causing the detector to fire every time a temporary spike occurs, only to resolve a few seconds later. You can address this by adjusting the evaluation window to encompass a longer duration or by applying a threshold that requires the condition to be sustained for a minimum number of consecutive data points. Instead of reacting to a single instantaneous value, you shift the focus to a rolling average or a more stable statistical representation of the signal. This approach effectively dampens the noise generated by short-term volatility without sacrificing the responsiveness required to detect actual sustained issues. By tuning these sensitivities, you allow the alerting engine to distinguish between meaningful service degradations and transient operational noise. In cases where an alert is truly stuck due to a broken internal state, manual intervention becomes necessary to restore production visibility. You can utilize the API to manually clear the event status for a specific detector, which resets the state machine to a healthy baseline. Before attempting this, however, you must ensure that the underlying issue causing the state to stick has been resolved within the metric stream itself. If you clear a state while the metric remains in the violation zone, the detector will immediately re-trigger, leading to an infinite cycle of manual resets that does not address the underlying problem. Always validate your current signal values against your threshold definitions before invoking an API clear command to ensure the system has a clean slate to begin fresh monitoring. This targeted remediation allows you to recover from corrupted states without needing to delete and recreate the entire detector configuration. Finally, you must consider the role of upstream pipeline delivery times in the context of alert latency. An alert might appear to be delayed because the metrics themselves are arriving at the observability platform behind schedule due to network congestion or ingestion pipeline bottlenecks. If you notice that your charts reflect events well before the alerts trigger, you should investigate the intake timestamps of your data points. Validate that your collector configurations are optimized for throughput and that no excessive processing rules are delaying the transformation of data. Understanding the end-to-end flow of your information is paramount, as an alert can only be as current as the data it is processing. By ensuring that your ingestion pipeline is operating with minimal overhead, you align your alerting capabilities with the real-time operational demands of your infrastructure. We have covered the fundamental strategies for maintaining healthy alert states through configuration tuning and API intervention. I will see you in the next session. Welcome back. In this chapter, we explore how to architect advanced population monitoring detectors that leverage dynamic statistical outlier analysis to identify anomalous components within your infrastructure. When we observe complex, distributed systems, we often find ourselves managing homogeneous groups of resources, such as a cluster of web servers or a set of microservice replicas. While individual monitoring is useful, it often leads to alert fatigue when you have hundreds of nodes scaling up and down. Instead, we use population outlier detection to ask a different question. Rather than checking if a single node has crossed a static threshold, we look at how a specific node compares to the collective behavior of its peers at any given moment. This approach is powerful because it inherently adapts to the baseline of your infrastructure. If your entire cluster starts consuming more CPU due to increased traffic, the detector recognizes this as a global shift rather than an anomaly. The logic centers on identifying which individual component deviates significantly from the statistical norm of the group, effectively filtering out noise that would otherwise trigger false positives in a standard threshold-based monitor. To implement this effectively, we must first configure the outlier detection condition within the detector settings, choosing the appropriate statistical derivation model. The Splunk Observability Cloud typically allows you to select between methods like standard deviation or mean absolute deviation to define what constitutes a deviation. Standard deviation is highly effective when your data follows a normal distribution, as it accounts for the spread of values around the arithmetic mean with high precision. However, if your dataset contains significant outliers or does not follow a bell curve, mean absolute deviation provides a more robust estimate that is less sensitive to extreme spikes. Choosing the right model depends on the nature of your metrics, such as latency or memory utilization, and how much variance you find acceptable before considering a node to be malfunctioning. Once the model is selected, you define the sensitivity threshold, which determines how many units of deviation are required to trigger an alert. A critical technical constraint you must respect is the minimum population size required to perform these statistical calculations. If you attempt to run an outlier detection on a group consisting of only 2 or 3 nodes, the statistical significance of your results will be fundamentally flawed. Calculating a mean or a standard deviation requires a large enough sample size to ensure that one rogue data point does not disproportionately skew the entire baseline calculation. You should set your monitor to ignore or suppress signals when the reported population size falls below a specific threshold, typically 5 or more nodes, to prevent erroneous alerts during redeployments or cluster scaling events. By enforcing these constraints, you ensure that the system only flags an anomaly when there is enough data density to justify the statistical conclusion. This is the difference between a high-fidelity monitoring strategy and one that results in erratic, untrustworthy notifications. Another essential technique is the use of group by parameters to segment your population accurately. In a modern cloud-native environment, you might be running thousands of containers across multiple distinct regions or availability zones. If you compare a web server in North America to one in Europe, their latency characteristics will likely differ due to geographical network distance. By applying group by dimensions, you segment the population so that the statistical analysis only occurs within a relevant context, such as by cluster, service version, or data center. This ensures that the dynamic baseline remains representative of the specific environment each component resides in. As the wider population baseline naturally shifts over time, perhaps due to a global update or a surge in user activity, the detector dynamically recalibrates. This creates a self-healing alerting policy that requires minimal manual tuning, even as your underlying infrastructure footprint expands or contracts. See you in the next lecture. Welcome back, as we delve into the mechanics of building resilient alerting systems that withstand the volatility inherent in modern distributed infrastructure. Alert flapping is a particularly insidious problem in monitoring systems where a metric oscillates rapidly across a defined threshold, causing a detector to transition between alert and OK states in quick succession. This behavior creates significant noise for on-call engineers, devalues the signal of legitimate incidents, and ultimately leads to alert fatigue. To prevent this, we must shift our design approach from simple threshold monitoring toward more sophisticated hysteresis models. Hysteresis involves defining two distinct threshold values, one to trigger the alert, and a secondary different value to clear it. By ensuring the metric must return to a more stable state before the alert can resolve, we create a buffer that effectively masks minor, transient fluctuations that do not represent a genuine service recovery. Another critical technique in our arsenal is the implementation of mandatory trailing evaluation duration windows, which force a metric to sustain a violation state for a specific period before an alert is triggered. When we configure a detector to look at a signal over time rather than evaluating a single instantaneous data point, we inherently filter out short-lived spikes that lack operational significance. This temporal requirement acts as a low-pass filter, ensuring that our monitoring logic reacts only to persistent changes in system health. If a metric crosses a threshold and immediately reverts, the evaluation window ensures that the alert state remains dormant, preserving your team's focus for events that actually require human intervention. In scenarios where metrics exhibit high-frequency noise or rapid jitter, moving averages provide an effective mathematical transformation to smooth the signal. By calculating a moving average of the metric over a defined lookback period, we attenuate the extreme values associated with transient oscillations while retaining the underlying trend necessary for accurate detection. This approach is mathematically sound because it replaces the raw, noisy input with a more stable representation that reflects the aggregate performance of the service. Once the signal is smoothed using this transformation, applying a standard threshold to the resulting series becomes significantly more reliable. It is important to balance the size of the window. A window that is too short may still allow noise to pass, while one that is too long might delay the detection of a critical failure. Tuning the sensitivity of your detectors is the final layer of configuration that bridges the gap between raw data and actionable intelligence. We must adjust the sensitivity settings to eliminate the loops caused by rapid firing and clearing cycles, often by recalibrating the boundary between normal and abnormal behavior. This typically involves identifying the natural variance of the metric during standard operating conditions and setting the detector thresholds outside of this observed noise floor. If a specific component consistently floats near your limit, it is often more effective to redesign the threshold logic or apply a statistical adjustment rather than simply raising the alert limit blindly. Consistent, thoughtful calibration ensures that your alert notifications act as a high-fidelity instrument rather than a source of persistent, distracting chatter. See you in the next lecture. Hello, and let us dive into the nuanced domain of monitoring cyclical patterns within your metric infrastructure. This chapter focuses exclusively on mastering the sophisticated techniques required to detect anomalies in data streams that possess inherent recurring behaviors. In many modern distributed systems, metrics are rarely static or purely random. They often adhere to strict temporal shapes driven by human activity or batch processing requirements. Consider a classic e-commerce platform that experiences a predictable spike in traffic every morning as users begin their day, or a back-end service that performs an intensive database reconciliation job every Sunday at midnight. When monitoring these systems, a simple static threshold is insufficient because the normal operating range fluctuates significantly throughout the day or the week. If you set an alert threshold high enough to accommodate the peak traffic, you miss subtle failures during the troughs. Yet setting it low generates a flood of false positives during standard operational hours. By employing historical anomaly detectors, we shift the responsibility of baseline calculation from manual intuition to an automated, data-driven process that understands the temporal context of your services. Throughout this chapter, you will learn how to configure these detectors to distinguish between expected rhythmic variations and genuine incidents, thereby significantly reducing noise in your notification streams. When configuring an historical anomaly detector, the primary task is to define the lookback window, which serves as the memory of your monitoring system. This window dictates how far back the Splunk Observability Cloud metrics engine analyzes previous time slices to construct a statistical representation of what constitutes normal behavior. If your metric follows a daily cycle, a weekly lookback window allows the system to compare the current metric value against the values observed at the same point in time over the last 7 days. It is critical to choose a window that aligns with the refresh rate of your cyclical business logic. For instance, choosing a window that is too short might fail to capture the nuances of a complex repeating cycle, while one that is excessively long might incorporate outdated telemetry that no longer accurately reflects your current system architecture. Once the look-back window is established, the platform calculates a moving average accompanied by dynamically adjusting standard deviation bands. These bands are essentially envelopes that expand and contract as the expected value changes throughout the day, providing a flexible safety net that wraps tightly around your legitimate traffic patterns. Tuning these detectors requires a measured approach, particularly regarding the sensitivity parameters that determine how wide the divergence from the baseline must be before an alert is triggered. You are essentially looking for an optimal balance where the bands are narrow enough to capture genuine anomalies, but wide enough to accommodate the natural variance inherent in any real-world production environment. If you find that your detector triggers during routine business hours, it is often necessary to adjust the standard deviation multiplier or the duration of the sustained threshold violation. This process of filtering allows the tool to ignore transient spikes that stay within the statistically calculated tolerances of previous cycles, focusing instead on true out-of-band behavioral changes. When you successfully isolate these authentic deviations, you gain the ability to pinpoint issues that are otherwise masked by the sheer volume of recurring high-traffic patterns. Successfully managing these detectors is not about setting a configuration once and hoping it holds, but rather about observing the performance of the alerts over multiple cycles and refining the parameters to account for changes in your service deployment patterns. As you work through your configurations, always ensure that your metric streams are consistent and that your lookback period is sufficiently populated with data. A detector attempting to calculate a baseline from incomplete or intermittent data will produce unreliable anomaly boundaries, leading to unpredictable alerting outcomes. Maintain a clear understanding of the difference between an outlier that indicates a systemic failure and a recurring peak that represents successful, intended operational throughput. By leveraging the power of historical lookback windows combined with dynamic thresholding, you transition your monitoring strategy from reactive to proactive, allowing you to observe deviations while the business rhythm continues undisturbed. This approach ensures that your operations teams are alerted only when the system truly deviates from its established historical identity. I look forward to discussing how these analytical patterns manifest in your specific service architectures in our next meeting. Welcome back. In this chapter, we will explore the architectural strategies required to monitor massive, large-scale infrastructure environments effectively. Monitoring environments that encompass tens of thousands of concurrent metric sources introduces unique challenges that go beyond standard detector configuration. When you deal with such scale, the primary goal shifts from merely collecting data to managing the computational cost of evaluating that data in real time. If you apply a detector to an unfiltered high-cardinality data stream, you risk hitting platform throughput limits, which manifests as alert evaluation latency or Worse, dropped signals. To avoid this, you must treat your metrics infrastructure as a tiered system where data reduction happens as close to the source as possible. We begin by considering spatial aggregation functions, which allow you to collapse individual metric streams before they ever reach the evaluation engine. By summing or averaging granular data points into a broader representation, you effectively reduce the number of time series the platform needs to track simultaneously. This is not about losing visibility. It is about choosing the level of granularity that is actually actionable for your monitoring requirements. When working with large-scale environments, applying global alerts to every single instance often leads to excessive noise or computational overhead. Instead, consider leveraging top-end filtering structures to isolate only the most relevant or degraded infrastructure elements. Rather than evaluating every node in a fleet of 20,000 containers, a top-end filter focuses the detector on the 10 or 100 instances exhibiting the most extreme behavior. This strategy significantly bounds processing requirements because the alert engine effectively ignores the healthy majority. You can further optimize this by implementing strict metric dimension scope constraints within your base signals. By explicitly filtering your signal flow to include only the necessary dimensions, such as region or environment tags, you prevent the platform from attempting to compute aggregates across an unnecessarily wide, high-cardinality data space. High-cardinality data pools are the silent enemy of reliable alerting in complex systems. If you send millions of unique time series into a single detector, the resulting matrix computation can easily exceed the latency budget allocated for a single alert evaluation cycle. This results in alert lag, where the notification arrives far later than the actual incident occurred. To manage this, you must be disciplined about how you define your metric dimensions. Avoid including highly volatile values, such as transient request IDs or unique process identifiers, within your persistent metric tags. If a dimension produces a new value every few minutes, the underlying data store experiences cardinality explosion, which degrades both query performance and alerting stability. By maintaining tight control over which metrics are treated as dimensions versus simple metadata, you preserve the platform's capacity to process your most critical signals with minimal overhead. Successful monitoring at scale requires a shift in mindset from reacting to individual event triggers to managing the overall health of the observability pipeline. Think of your detector configuration as an implementation of a business rule that balances precision against resource consumption. If you find your latency spiking, look first at the number of time series entering your SignalFlow program. Often, a simple adjustment to the aggregation logic or the removal of redundant dimensions will alleviate the load without sacrificing the integrity of the alert. Remember that the platform's alerting engine is a shared resource, and efficient detector design is a collaborative responsibility between the engineer and the system. By pre-aggregating data and narrowing your scope, you ensure that even when your infrastructure expands into tens of thousands of nodes, your observability remains responsive and accurate. Always test your detector impact in a sandbox or via non-prod metrics before rolling it out to a global production footprint. See you in the next lecture. Welcome to the chapter on ephemeral infrastructure, where we will examine strategies for maintaining signal integrity when your monitored assets frequently appear and disappear. We will focus on designing alerting patterns that remain stable despite the volatility of modern autoscaling environments. When dealing with infrastructure that exists only for minutes or hours, traditional static alerting often fails. If you tie an alert threshold to a specific instance ID, you are essentially setting a trap for yourself when that instance scales down and is terminated. The first step in addressing this is moving away from host-specific identifiers toward abstract service identifiers. By using metadata dimensions, you group disparate ephemeral nodes under a unified logical entity, perhaps an application or a microservice version. When a specific container dies, the alert remains attached to the aggregate service metric rather than pointing to a non-existent host. This architectural shift prevents the common pitfall of alert storms generated by routine autoscaling events. You must ensure that your labels provide enough context to differentiate service versions without injecting high-cardinality metadata that could overwhelm your storage backend. Managing active tracking for these transient objects requires an intentional cleanup strategy within the observability platform. In Splunk Observability Cloud, you can implement detector behaviors that automatically purge tracking for inactive metrics after a predefined period of silence. Without this, your metric catalog becomes polluted with stale time series data from instances that no longer exist, which complicates capacity planning and user navigation. I always suggest setting these cleanup thresholds to align with your expected infrastructure churn rate. If a node is intended to live for no longer than 30 minutes, there is little utility in maintaining its specific granular data points indefinitely. Automating the expiration of these series keeps your workspace clean and ensures that your alerting environment reflects current reality rather than historical ghosts. Dynamic population-based alerting models serve as the foundation for stability in these environments. Instead of watching a static value on a single node, you apply an evaluation across the entire population of instances belonging to a specific cluster. For example, if you are monitoring CPU utilization, you evaluate the average or the percentile across the entire dynamic group, not individual hosts. If the aggregate value exceeds your threshold, the notification remains meaningful because it addresses the service health rather than an isolated server event. This approach naturally handles the arrival and departure of new participants in the cluster. Because the alert is defined by the population, adding or removing nodes merely changes the sample size, allowing the detection logic to continue operating without manual intervention. Finally, you must consider the temporal nature of your thresholds when life cycles are brief. If your instances cycle through their life cycle every 30 minutes, a detection logic that requires an hour of historical context to trigger will never function correctly. You need to configure short duration thresholds that match the shorter life cycles of your serverless functions or ephemeral containers. It is essential to choose windowing functions that are granular enough to catch anomalies quickly, yet robust enough to tolerate the momentary noise found in startup sequences. By aligning the alert's temporal constraints with the actual behavioral patterns of your infrastructure, you achieve a higher signal-to-noise ratio. Mastery of these timing parameters is what separates amateur configurations from production-grade observability deployments that effectively manage transient compute resources. See you in the next lecture. Welcome back. We are now moving into the realm of advanced signal flow controls for our ephemeral infrastructure monitoring needs. When we talk about signal flow, we are discussing the programmatic interface to the Splunk Observability Cloud Analytics engine. While the point-and-click interface is excellent for most standard operations, it eventually hits a ceiling when you need high-fidelity, custom telemetry streams. By writing raw signal flow scripts, you gain the ability to manipulate data streams at the source before they ever hit the visualization layer. This is not just about convenience. It is about performance and precision. By nesting analytical functions within a single expression, we reduce the computational overhead that arises when creating multiple intermediate data streams that might otherwise be calculated redundantly. Think of this as the difference between a declarative request and an imperative execution plan, where you strictly dictate the order of operations to the backend aggregator. One of the most powerful features you will encounter is the ability to adjust data delay and custom rollups directly within your code blocks. By default, the system applies standard resolution strategies, but in an ephemeral environment where nodes spin up and down rapidly, the default may introduce unacceptable latency or smoothing that hides transient spikes. You can manually set the rollup parameter to ensure that you are gathering data at the exact granularity required for a specific detector. For example, if you are monitoring a high-frequency event stream, forcing a raw rollup index ensures that no data points are aggregated or averaged into insignificance before your alerting logic gets a chance to evaluate them. This level of granular control is effectively the only way to catch microbursts that would be smoothed over by the default bucket settings. Managing processing resources effectively requires a disciplined approach to how you structure your syntax execution paths. When you write complex scripts, remember that each function call consumes compute cycles, and redundant filtering or unnecessary transformation steps will compound linearly as your metric volume increases. A clean, optimized signal flow script keeps the stream as flat as possible, applying filters as early in the chain as logic permits to minimize the number of source time series that the backend must traverse. If you are calculating complex derivatives or running percentiles against a high cardinality set, always move the most restrictive filter to the innermost processing layer. This ensures that the engine spends its budget on the data you actually care about rather than performing expensive math on discarded or irrelevant telemetry samples. Binding these signals directly to enterprise dashboard elements is the final step in the lifecycle of a high-performance alert. By using the program ID generated by your script, you can inject highly customized charts into your dashboard environment that behave differently than the standard canned widgets. This is especially useful for ephemeral infrastructure where the set of contributing sources changes every few minutes and a static chart would quickly become stale or inaccurate. You can code the logic for dynamic group by clauses or conditional thresholds that adapt to the current state of a cluster without requiring manual updates to the dashboard configuration. It creates a self-healing visualization layer that evolves in tandem with your underlying infrastructure, ensuring that your observability platform remains a source of truth despite the inherent flux of cloud-native systems. I will catch you in the next session. Welcome back. In this session, we will discuss advanced navigation techniques within Splunk Observability Cloud to streamline your daily monitoring workflows. When managing large distributed environments, your ability to traverse the system efficiently often determines the success of a root cause analysis. Navigating between vast infrastructure maps can feel overwhelming if you rely solely on manual searching or static dashboards. The platform provides global tag-based search capabilities that allow you to isolate distributed resources based on their metadata rather than their physical location. By utilizing the platform metadata catalog, you can move beyond simple name-based lookups to uncover component relationships that might otherwise remain hidden. This is particularly useful when dealing with ephemeral instances that appear and disappear rapidly within your infrastructure. Once you locate a specific resource, the contextual sidebar panels provide an immediate audit of active alert states without requiring you to switch views. Understanding how to link these disparate data points into a cohesive investigation flow is central to mastering the Observability Cloud interface. You should view these navigation pathways not just as features, but as integrated tools designed to maintain your mental model of the system during a high-pressure incident. Infrastructure maps serve as the foundational view for visualizing the health of your services and hosts at scale. Within these maps, you can configure filtering logic that segments your view by specific tags, such as service name, environment, or cluster origin. If you have defined custom metadata, you can apply these tags globally to ensure that your view remains consistent across different areas of the workspace. When you click on a node within an infrastructure map, the associated sidebar reveals critical telemetry data, including recent alert occurrences and key performance indicators. Efficient navigation requires that you practice these clicks until they become muscle memory, as this allows you to dive deep into a problem without losing your wider perspective of the system's state. I recommend organizing your most frequently accessed views into personalized workspace landing pages to avoid unnecessary navigation steps. By tailoring your dashboard groups to mirror your specific operational domains, you significantly reduce the mean time to discovery for any anomalous behavior in your stack. The platform metadata catalog is frequently underutilized by new users who tend to rely on predefined dashboards. Instead of searching for a visualization, you should search for the entity itself, and then let the catalog guide you to the relevant metrics and alerts. This workflow ensures that you are always looking at the most relevant data for the specific component under investigation. You can discover hidden relationships by inspecting upstream and downstream dependencies that are automatically mapped based on ingestion patterns. If a service is reporting higher latency, traversing the metadata catalog allows you to immediately see if that service is constrained by a specific host or container tag. This logical mapping helps you avoid the common trap of making assumptions based on incomplete visibility. When you navigate through the metadata, you are effectively exploring the graph of your infrastructure, which is far more powerful than navigating through a folder structure of static files. Configuring your workspace is not merely a task of aesthetics, but one of functional necessity for effective troubleshooting. A well-configured landing page should act as your control center, surfacing the most critical alerts and health metrics immediately upon login. By customizing the layout to prioritize specific dashboard groups, you create a dedicated space where your primary operational needs are highlighted. Consider what information you need to see within the first 60 seconds of entering the platform during an outage. If you are responsible for multiple microservices, group them by their life cycle or business function rather than their infrastructure type. This abstraction layer protects you from the noise that is inherently present in large-scale monitoring environments where thousands of signals are produced every minute. Taking the time to optimize your workspace layout demonstrates a proactive approach to system maintenance, ensuring that the platform works for you rather than against your objectives. In high-pressure situations, the ability to jump between related entities using tags and breadcrumbs is vital. When you are auditing an active alert in the sidebar, you must be comfortable transitioning from that alert state to the actual signal visualization without losing your search context. This keeps your investigation tethered to the original trigger while allowing you to drill down into the underlying metric changes. These advanced navigation interactions prevent the cognitive load associated with opening multiple tabs or losing track of the service that originally threw the alert. Remember that navigation in the Observability Cloud is a journey through your own instrumented data, and the paths you take should serve your specific logical requirements. By mastering these connections, you ensure that you stay focused on the resolution of an issue rather than the mechanics of the interface itself. See you in the next lecture. Welcome back. In this lesson, we will establish the foundational concepts of application performance monitoring to prepare you for the challenges of analyzing complex, distributed architectures. Application performance monitoring, or APM, represents a shift from observing static infrastructure metrics toward understanding the dynamic flow of transactions through a polyglot, distributed system. While infrastructure monitoring tells you that a specific server node is consuming 70% of available CPU, APM provides the context of why that consumption is occurring. It bridges the gap between low-level hardware utilization and the actual user experience by tracking requests as they travel across service boundaries. Instead of viewing isolated logs or memory usage spikes, we gain the ability to visualize how a single customer request triggers a chain reaction of database queries, downstream API calls, and external service interactions. This visibility is essential for maintaining service-level objectives in modern environments, where transient microservices often obscure the root cause of performance degradation. By identifying these patterns early, you can optimize your system design before minor bottlenecks escalate into widespread service outages. At the heart of modern APM lies the mechanism of distributed tracing, which functions by attaching a unique span context to every piece of work performed during a request lifecycle. Each span acts as a discrete unit of logic, capturing metadata such as start times, durations, and specific attributes like the current host or database connection string. When these spans are propagated across service boundaries, they form a unified trace tree that reveals the true latency profile of your application. You might observe that while a service appears performant in isolation, the cumulative delay introduced by network hops and serial processing in the trace reveals a significant latency penalty. Understanding these mechanics is not merely an academic exercise, but a practical necessity for debugging asynchronous patterns where traditional request response logs fail to capture the full picture. By interpreting trace data, you can isolate where a request is queuing for resources versus where it is actively processing instructions. Service maps represent the geometric heart of a healthy APM strategy, offering a visual topology of how your services communicate with one another in real time. Rather than relying on static documentation that inevitably drifts from the reality of your deployed code, these maps are auto-generated from traffic flow data to show active dependencies. When you inspect a node within a service map, you are essentially looking at an aggregated view of performance characteristics like request volume and error rates for that component. If a particular edge between two services turns red, it indicates an influx of HTTP 5XX errors or significant latency deviations that suggest a hard dependency failure. Analyzing these maps allows you to identify circular dependencies or unexpectedly high traffic volume between services that should otherwise remain decoupled. It transforms the daunting task of scanning millions of log entries into an intuitive process of visual pattern recognition. To make actionable decisions, you must master the fundamental performance triad: request volume, error rates, and response time metrics. Response time is often the most nuanced, as it requires you to distinguish between server-side processing overhead and the latency incurred on the client side or within the network transport layer. A high response time might be reported, but if the error rate remains low, you are likely looking at a resource saturation issue, such as thread pool exhaustion or database lock contention. Conversely, an increasing error rate with low latency is a classic indicator of configuration errors, authentication failures, or incompatible API contracts between services. By correlating these APM metrics with your existing infrastructure signals, such as disk I/O or ingress throughput, you gain the ability to pinpoint whether an anomaly is rooted in application logic or faulty provisioning. This correlation is the primary tool for reducing mean time to recovery in high-velocity deployments. Utilizing out-of-the-box dashboards is your first line of defense when navigating microservices performance anomalies within the Observability Cloud. These pre-configured displays are designed to surface the most critical operational indicators without requiring you to manually define every query or metric transformation. They consolidate viewpoints that aggregate data across disparate services, allowing you to filter by specific environment tags, data centers, or service tiers to isolate the scope of an incident. While customization is powerful, the default dashboards provide a baseline of health that highlights when your baseline for normal behavior has shifted. Learning to interpret these views effectively means recognizing how the platform translates raw ingestion data into meaningful business context. As you become more proficient with these tools, the correlation between trace-derived metrics and infrastructure health will become second nature to your workflow. See you in the next lecture. Welcome back to our exploration of observability workflows. Today, we focus on the systematic process of diagnosing latency bottlenecks to maintain high-performance services. When users report that a service is slow, the immediate reaction is often to check the application code or the database. But latency is generally a symptom of a deeper structural or environmental constraint. To effectively isolate these issues, you must adopt a top-down approach that correlates application-level behavior with raw infrastructure resource consumption. We start by observing latency, errors, and traffic, often referred to as the golden signals, to pinpoint which specific service or endpoint is experiencing degradation. Once we identify the problematic component, we look for evidence of exhaustion in the underlying infrastructure, such as CPU saturation. Welcome to our final review session for the SPLK-4001 certification. We are here to consolidate your knowledge and prepare you for the exam experience. As we step into this final synthesis of the course, we must address the core domains that constitute the blueprint of the Observability Cloud Metrics user exam. You have already navigated through the complexities of OpenTelemetry ingestion, where we focused on the architecture of collectors and the specific configuration of processing pipelines. It is essential to remember that ingestion is rarely a set-and-forget task. The accuracy of your metrics depends entirely on the precision of your processing rules. When you encounter questions regarding metric types, consider how gauge, counter, and cumulative values behave under different reporting intervals. Understanding that rollups are not merely aggregations, but lossy transformations of high-resolution data is critical for any scenario involving long-term trend analysis. If a question asks about data granularity, always look for the relationship between the ingestion frequency and the resulting rollup window. Your ability to distinguish between these behaviors often separates a passing score from a failing one. Moving beyond ingestion, we shift our focus to the visualization and alerting layers that form the user-facing side of Splunk Observability Cloud. Many candidates struggle with the nuances of dashboard design and the practical application of SignalFlow. So let us solidify our mental map of these components. When you are tasked with creating custom dashboards, always prioritize the logical grouping of dimensions, as this directly impacts the performance and clarity of your charts. Remember that your choice of visualization, whether it is a heat map, a line plot, or a statistical table, should be dictated by the underlying cardinality of the data. High cardinality is a recurring theme in the exam, and you must know how to mitigate its impact by using appropriate filtering and aggregation functions. When configuring alerts, the distinction between a simple threshold detector and a more complex signal subset detector is often the difference between actionable notifications and alert fatigue. Never neglect the power of muting rules, as they remain your best defense against predictable, noisy events in ephemeral environments. Analyzing advanced analytics requires a firm grasp on the mathematical transformations available within the platform. You should be prepared to identify the correct usage of functions that compare time windows, such as shifting a current signal against a historical baseline to detect anomalies. Ratio analysis and percentage-based calculations are frequently tested as a means to observe healthy versus unhealthy throughput. So ensure your understanding of floating point operations within the signal flow context is solid. When we talk about population outlier detection, we are looking at identifying statistical deviations that deviate significantly from the norm within a group of high-dimensional metrics. These detectors are built on top of your existing metric architecture, and they require clean, metadata-rich data inputs to function reliably. If you find yourself overthinking a diagnostic question, return to the fundamental properties of the metrics, such as their source, environment, and specific dimension keys to prune incorrect answers. Finally, let us discuss the test-taking strategies that will serve you best during the actual examination environment. Time management is often an overlooked aspect of certification prep, yet it is just as crucial as your technical knowledge for this specific exam. Do not linger on a challenging question regarding complex signal flow syntax. Mark it, move on, and return only after you have secured points on the more straightforward dashboard configuration questions. The exam designers often include extraneous information to test your ability to filter noise, much like an effective detector filters out non-critical alerts. Stay calm, read the scenario requirements twice, and look for keywords that define the scope of the problem. You have the technical foundation required to succeed. So trust your experience with the platform and your intuition regarding how data flows from source to visualization. See you in the next lecture.